working.
I figure we'll wait probably like 5 minutes to let everyone get in.
I saw some people trying to navigate the buildings.
Okay, yeah. Since the keynote went long, makes sense. Hopefully this talk will be a little bit short.
If I start the HPC mini after for a couple of minutes longer, it is short as well. It's 5 minutes.
Yep, sounds good.
I think the rate at which people connect seems to have decreased.
Where's my cursor?
The top middle.
Thank you. Con. Yes. I just need it back to restart it. Okay, there we go. Okay. So I figure we can get started. Let's see. Okay, so thank you very much for coming. This work was done in collaboration with a bunch of other people at both Julia Hub and the University of Washington. Fortunately, I couldn't list them all here, but thank you very much if you know who you are. Their help is essential in getting Julia to fly, quite literally. So to illustrate where I'm going with this, I wanted to play a quick little video. This is Julia running on the quadcopter. It's being used in closed loop here to run a 3-degree of freedom controller. The microcontroller that's actually flying the vehicle here is communicating a state estimate to Julia, which is then responding in real time to produce an acceleration demand that's causing it to fly in this circle. I'll be talking about two different implementation strategies that we took to get this working. One is what you're seeing here, and I'll talk about it in a second. And I'll also talk about some of the challenges that we faced along getting Julia into an embedded real-time environment. Okay. So I think that at this point we're all quite familiar here with Julia's arguments about solving the two-language problem. The idea is that Julia can give you like high productivity and high performance in the same language, et cetera, et cetera, et cetera, the old story. Normally when we talk about that though, we're talking about solving it in like a desktop-like or an HPC-like environment, maybe a little bit of GPUs on the side. At the same time, you see these same sorts of problems embedded in real-time control applications. You see a lot of people who are working in very high-level languages who then have to sort of fight to then get their algorithms or the implementations down onto the actual controller or the actual embedded platform that's ultimately controlling the system. And what we were interested in doing is asking is, can we use Julia to solve this kind of two-language problem? Can we use Julia to solve the two-language problem that we're getting in the embedded space? And today I'll talk about some proofs of concept for that. But as I say, like embedded real-time controller, there's sort of two descriptors there. There's two adjectives there that are worth discussing in a little bit more detail. So the first one is embeddedness. There's a lot of embedded computers out there, and there's sort of no single concept of what an embedded computer is other than it is a computer that is shoved into something else. They come in a wide array of form factors. So like on one end of the spectrum, you have what are basically, which orientation is this? On one end of the spectrum, you have what are basically just normal computers that are shoved into a ruggedized box. They have some funky connectors on them, but they're ultimately desktop class or server class hardware, tens of gigabytes of RAM, the normal OSs and CPUs you're used to dealing with. Julia can actually be used on these quite readily. It's basically a normal computer in a funky box. You then have more embedded platforms, stuff like Raspberry Pis. They have much smaller processors. You're talking about things on the order of gigahertz. They have lower IPCs at that. They have less RAM. They have less memory, but they're still desktop-y systems. These are commonly referred to in the embedded world as application class processors. They have MMUs. They can run Linux in simultaneous multiprocessing environments. They're still desktop-like systems. You can think of them like a normal computer, but they are easier to embed into larger systems. Then on the other side of the spectrum, you have microcontroller-like things. These are processors that are much simpler to implement into your system, and they also achieve much better real-time guarantees. But for that simplicity, you're paying a lot in terms of performance. So the sort of higher end of microcontrollers these days are talking 500 megahertz to 1 gigahertz. You're taking an even bigger IPC oof when you go down to these. And we go from talking about gigabytes of RAM to talking about megabytes of RAM and storage. And then on the very far end of these, we have like this image here is of the new like packaged world's smallest microcontroller from Texas Instruments. These things are still running like tens of megahertz. Kilobytes of RAM and are obviously extremely easy to implement, but for that you're paying a lot in terms of the amount of performance. And sort of what I'm interested in talking about today is how can we get Julia onto this whole wide spectrum of devices. Another qualifier that I mentioned was real time. There's sort of two aspects to this. I'll talk about both of them. And it's also extremely fuzzy. So the one way you can classify these real-time systems is based on what goes wrong if you don't meet whatever definition of real-time you have. So like on one end of the spectrum, you have stuff like video games. It's important that a video game gets back to you quickly, or else you have the frame will stutter. But it's ultimately annoying. Like it's kind of okay if you drop from 60 FPS to 51 FPS in a video game. No one cares that much. On the other hand, on the other side of things, you then have hard real-time systems where if it goes wrong, if it misses that deadline, then everything goes to hell. So in this example that I'll be talking about today of the quadcopter, if our translational controller suddenly takes you 1 second to get back instead of 10 milliseconds, the quadcopter will go into a wall. And that's not a desired outcome, and it's relatively low stakes here. Hard real-time systems can get a lot trickier than this. For example, in electrical control, if you miss a microsecond deadline, you might be talking about getting 24 volts through on a 3.3 volt bus, and nobody likes that experience. That said, this taxonomy, like you'll hear these terms a lot. This taxonomy is really fuzzy, depending on who you're talking to and what domain they're working in and what context it is. All of these will be different. Another aspect to this real-timiness is the time scale that you're working at. You can go from nanosecond latency, you'll see these sorts of requirements in like RF direct digital synthesis or optical systems, all the way up through to hectosecond time delays. And all of these are still real time, they're just different definitions of what it means to be real time, driven by when you need to get the answer back. Let's see, right. Okay, so to quantify this a little bit for this specific talk, I'll be talking about flying the University of Washington Autonomous Control Laboratory quadcopter using Julia. There's two different major processing devices that are available on this platform. One is a Raspberry Pi CM4. It has a quad-core application class processor like I mentioned earlier. It's running Raspberry, and I'll talk about this in more detail later. So this is sort of acting as a sort of higher level computing platform. The lower level computing platform, the thing that actually does the hard real-time control on the quadcopter for the most part, is the STM32H745 microcontroller, which has a Cortex M7 running at 480 megahertz. This is, as I mentioned, a hard real-time application because if the controller doesn't get back to you in a lot of time, the quadcopter goes into a wall, and the quadcopter does not enjoy this experience. Ask me how I know. For this application, our control loop is running at 100 hertz, so we'll have about 10 milliseconds. 10 microseconds is very different in order for a controller to be able to meet its deadlines. In terms of broad software architecture, the low-level drone control is being done, and as well as state estimation is going to be done by the standard PX4 autopilot. The way that all of these systems that I'll be presenting today work is by having PX4 produce a state estimate that's then sent across to Julia through some mechanism. The vagueness is intentional here. And then Julia will compute a desired control output and send it back to PX4 to be executed by the quadcopter. The flight plan for all I'll show you today is to fly in a circle. This is a very sophisticated, complicated trajectory described by 3 lines of code. We're doing position, velocity, acceleration control in 3 degrees of freedom, and then the attitude control of the quadcopter is then handled by the built-in PID controllers running on the microcontroller in PX4. So we're just producing a thrust demand here. We're not doing attitude control at this point. The control law is a very straightforward geometric controller. It's actually literally implemented in 1 line of code. The throttle is calculated as the desired throttle is calculated as a function of the position error, the velocity error versus the feed forward. We also produce have a gravity feed forward term, and then it tries to track the desired acceleration. We then finally have a projection onto the orientation of the quadcopter because of the differential flatness to make sure that we don't go flying off in totally the wrong direction. So the first architecture that I'll be talking about today is actually not an embedded one at all. This is software in the loop. So here, what's happening is that I have the controller that's running in Julia on a normal REPL on my normal desktop with all the normal web browser-y stuff that's going on in the background on the same desktop. It's then communicating over UDP via loopback and the Xeno messaging middleware through a router and then to the PX4 flight controller, but this time also running on my desktop. PX4 then has its own CIDL support that then allows it to control a virtual drone rather than a physical drone. And then it's then sending those updates to the gazebo simulation that is then simulating the drone in 3D, and then that state is then being propagated all the way back through PX4 all the way to Julia. So there's quite a long round trip all in a not real-time environment happening here. And you'll see why I'm adding all of these qualifiers in a second. So for an example of what the trajectory ultimately looks like, and you'll note that the circle changes size through most of this. What we do is the drone will start at an initial position, and then it will sort of start tracking the circle. And here, because the gains are sort of tuned down a little bit to keep the drone from being too aggressive, we're getting close, but not perfectly tracking it. So the reason why I mentioned the not real-timiness is as an example of the performance that we get in this setting. when we have the built-in controller running, so this is running in PX4, which is then removing all of this, a lot of the scheduling and the networking stack out of the equation, we're seeing that there's like 0.7 milliseconds of variance, which is reasonable in this setting. Again, we have a 10 millisecond budget here. Where it gets a lot more exciting is when we switch over to the Julia controller running in the REPL, when the outliers are starting to get concerningly close to that 10 millisecond budget, and our variance overall is about 2 milliseconds of delay. A lot of this is then likely coming from running on a normal desktop with all of the normal background applications. So, but at the same time, that desktop is a lot more powerful than the Raspberry Pi, for example, that we'd be implementing on. So, early on, there are some interesting challenges, let's say. So let's talk about that first implementation onto the Raspberry Pi. The architecture that we're using on board is ultimately extremely similar to the one that we're using in the CITL simulation, quite intentionally. Except here, instead of having both PX4, the underlying flight controller, and the Julia flight controller running on the same physical hardware, we're splitting them. Now, the Julia flight controller is running on the CM4, the Raspberry Pi, connected via Ethernet to the microcontroller that's then running the low-level flight controller. The low-level flight controller is then sending state estimates back over Ethernet to Julia. Julia is then doing its computation and then sending the command acceleration back to PX4 to actually execute. The way that we're calculating timing in this setting is that we're running a hardware timer on the microcontroller. So the microcontroller, when it sends a state estimate back to the CM4, is starting a hardware timer running at the clock speed of the microcontroller, and then when it gets that acceleration demand back, it then stops that and records that. So that's how we're measuring the timings. Getting this to work had some interesting challenges. So like I mentioned, we're running on a Raspberry Pi Compute Module 4. It's essentially Raspberry Pi 4 and a slightly more embedded application. We're running Raspbian without special real-time extensions. So it's normal Linux. We're not running RT Linux here. We wanted to avoid like running the JIT. We wanted to avoid running the GC, and we coded for this, but we wanted to keep the size down because our Raspberry Pi is not actually a very good one. We only have about 2 gigabytes of free memory on board the platform, and we wanted to do as much of the compilation off-board as possible. So the solution that we adopted to that was JuliaC, which ended up working quite well. I won't go into too many of the details for how we did this. If you're interested in more details on JuliaC, please see Jeff's talk later today on trim. Some of the specific challenges that we ran into that I want to talk about, though, is that Julia doesn't currently support cross-compilation. You need to run JuliaC on the same architecture that you're targeting. My computer that I did this work on is x86-64, and the Compute Module 4 is running AArch64 ARM. The solution that we came to was we compiled this using a GitHub Actions ARM runner. If you're interested, the GitHub CI setup is available online. I'll have this again at the end of the talk if you're interested. This sets up all the dependencies and compiles it with some caveats that I'll talk about at the end, though there are some works. So in particular, you have to set up the artifacts by hand, and it would be nice in the longer run to produce a Docker image that you could just sort of set up and run that has everything built in. So ultimately, what we were able to do is we were able to take the Julia code that we had and then compile it down to a 2.2 megabyte binary plus about 160 megabytes of runtime dependencies that were pulled in by Julia to make it all work. We likely could trim this smaller, but this was small enough to fit on the Raspberry Pi with room to spare, so we were happy with this. So I just also wanted to add some really important caveats here before I present the timing results. It's measured on the microcontroller, and it also includes networking latency, so the latency required to get from the microcontroller to the CM4, the non-real-time Linux execution on the CM4, and then the serialization and deserialization overhead that's happening both in Julia and in the microcontroller. Does this work? So yeah, so this is just the earlier. This is just the earlier video that I showed you. So this is running with this drone here is being controlled through the architecture that I mentioned. The Raspberry Pi is physically on the drone, communicating to it over Ethernet, and then driving it around in a circle. And let's see, I think. Right. So then the timing for this one, despite the fact that the Raspberry Pi is noticeably less powerful than my desktop by a considerable margin, the timing for this was considerably better. We were able to achieve a median response time of about 6 milliseconds, which is somewhat of an improvement, but we have a more comfortable margin between the timing outliers and our 10 millisecond timing budget. Additionally, we reduced our overall response time variance by about a factor of 2. So we went from about 2.2 milliseconds to 1 millisecond of response time. One note that I would make here with this particular graph is that the initial controller, the built-in controller, is being based on a different position estimate that's coming out. This will cause the built-in controller, the one that's stock with PX4, to always show up at about the 10 millisecond line because it's running one control loop out of phase. So the reference here should be made to that 10 millisecond line rather than 0 milliseconds. The next architecture that we looked at, that we got Julia running in, is actually running Julia on the microcontroller itself. So this is running Julia on the Cortex M7. Here we eliminate all of the networking. So it's actually being built into the same executable that PX4 is. It's just running as part of the PX4 system, as part of the NetX real-time operating system. And the compilation approach that we adopted here is very much inspired by MCU compiler, based on static compiler, and is built on top of the GPU compiler infrastructure. Getting Julia to run on the microcontroller was a bigger adventure than Trim. Getting Julia to run with Trim was pretty easy. We had to work on some small features, but it ultimately fairly straightforward. Getting it to run on the microcontroller took more work. We needed a specially compiled version of Julia. Julia doesn't normally come with the ARM v7 target that you need to get it to run on the Cortex M7. And the floating point support in LLVM on Cortex M7 or ARM v7 has some interesting warts. In particular, despite me thinking that it says hard float in it, the thumb M7 none EABI HF does not actually make it generate hard floating point instructions. So that was a bit of fun. And we ended up having to use LLC directly because because LLVM doesn't expose this very well through the API. Let's see. The ultimate architecture that we ended up with for compiling to the microcontroller target takes Julia, sends it through static compiler. We end up with LLVM IR in a textual format, which we then compile with LLC into a 1.5 kilobyte executable. So this is really, really small and fits into the 2 megabyte overall program memory quite nicely. We then statically link that using normal GCC LD in with the rest of the PX4 flight controller code, as well as the shim that intermediates between Julia and the rest of PX4. And then we end up with the native executable. It's not perfectly 2 megabytes. I think it's like 1.995 megabytes, but again, I'm quite happy with that. We have 2 megabytes of memory. Let me play this. Yeah. So this is the drone flying Julia on the microcontroller. So it again starts, the circles, has changed size and position a little bit. But here it's able to successfully track the trajectory. It works, ultimately. Right, so timing on this. Now that we've managed to eliminate most of the overheads, the performance on the end-to-end performance on this is a lot nicer. Despite the fact that the microcontroller is a lot slower, to put it mildly, than the CM4, because we're able to avoid the networking overhead, the non-real-time OS, all of the things I mentioned earlier, it becomes so fast it's actually quite hard to measure on the microcontroller. The mean of this was about 7,000 clock cycles, and the minimum, so probably the actual execution time if we didn't have RTOS interrupts happening, et cetera, in the interim was about 4,000 clock cycles. And obviously the variance also drops dramatically because there's frankly a lot less time for exciting events to happen. So in conclusion, you can use Julia in real-time on embedded systems. There's a couple of ways you can do it. We're able to achieve both millisecond level latency through a network-based approach using Julia on a companion computer connected to a microcontroller, as well as microsecond level latency by running Julia directly on the microcontroller. You can deploy Julia onto application class hardware in a very straightforward way, in spite of relatively constrained memory for application class hardware. If you're interested in more details on that, check out Jeff's talk. I'll have links to my work on the next slide. the results were way faster and smaller than package compiler. Like JuliaC was able to compile our code here in seconds versus when I tried to do this with package compiler, which I don't think actually finished. Another thing that I want to mention, and if you're interested in this, is that Julia has a lot of opportunity to work very well with ROS. As part of implementing this, we implemented a native Xeno binding, and we think that we can get Julia working extremely cleanly with ROS. If you're interested in more details on this, please talk to me afterwards. Following on from that, deployment onto microcontrollers directly is possible, but it's still pretty immature. So we had a number of issues along the way. In particular, floating point support on ARM v7 needs some work in order for this to be widely usable. Though experiences, if you're using a much more modern microcontroller that runs ARM v8m, might be better. So finally, just to wrap up, the code is available here. You can go to, if you just search these on GitHub, you should find these examples. I would suggest that if you're interested in this, you should probably actually look at the application class example, but the microcontroller example is still very proof of concept level rather than something that I would suggest that you think about production with. Okay, thank you very much. Any questions? Yes?
Yes, thank you.
Please wait for the...
Thank you. Regarding Julia on the microcontroller, did Julia have to communicate with the sensor hardware and the motor hardware through I2C, SPI, or others, or was it isolated from that?
So in this application, it's isolated by the driver stack provided by PX4. So we're actually a couple of levels abstracted from that. PX4 is doing the low-level I2C and SPI support. So in this particular application, all of our sensors are SPI-based. That's then filtered by the C++ extended Kalman filter built into PX4, which is then producing the state estimate that we're using. That's also doing fusion from the vision system you saw in the pictures. So we're not doing ultra low level stuff like that yet.
Even when Julia was on there?
Correct.
I have a question about the cross compilation.
Yep.
Are you aware of any even experimental things in the works that would allow you to do cross-compilation on Julia?
I'm not sure. I wouldn't be the person to ask. If you're interested in that, talk to maybe Cody or Jeff.
All right, thanks.
How hard was it to get GitHub Actions to get the right target that matched what you needed to build to do the compilation for your architecture?
Super easy, actually. Let me... let's see. Yeah, okay, so the two things that were needed was this line, which makes it use the GitHub Actions ARM runner, and this line, which makes Julia pick the right ARM target. That was all. So this was by far and away the easy part.
Do you have to write like special Julia code for this, or it's like generic way of doing regular Julia code?
Right. The trim code, like the JuliaC code, that I would say is just you are very careful about performance brain. Like you need to be careful about your allocations. I strongly recommend if you're in real time you not. And but ultimately you're aiming for sort of a very normal target of no dynamic dispatch, very carefully managed allocations, that sort of thing. So fast Julia code would be what would be for JuliaC. For the microcontroller, completely different ballgame. You need to like change your brain to think embedded in microcontroller rather than normal Julia. I think that's one of the big questions about like going forward with targeting MCUs is how can we exploit aspects of the Julia ecosystem to avoid having you to completely change the way you think in order to live within the constraints of the hardware.
So for the MCUs, you get rid of dynamic allocation completely?
Yes.
Or it's
Yeah.
still there?
So it's the same pipeline that's used for GPU kernels, for example. So they're completely allocation free. Any other questions? All right, thank you very much.
Yes, you're.
Is there USB-C?
Um,
Okay, so we're gonna, we need a USB-C thing. It's gonna, you know, it's technology, it's a thing. Great, delightful, delightful. And then we have to see if if my computer can handle screen sharing, which will be a whole fun ordeal.
so while you're setting that up,
Something's happening, this is exciting. Ooh, fancy. Okay.
I guess while we're debugging, I can like officially start the Julia for HPC mini symposium. Also, the organizers have put in a just-in-time panel at the very end. Sorry?
Does it need to speak to the mic?
I guess I should speak to the mic. So the organizers have, you know, in the spirit of Julia, set up a just-in-time panel at the end of the mini symposium. So that's at, excuse me, I think it's at 4 p.m. So I also invite the speakers to you know, participate in this panel, and then it will be like, you know, a nice panel where the audience and the speakers can discuss Julia for HPC more generally. I'm afraid I have to now make jokes. I don't know.
I need to figure out how to lower the resolution on my computer.
Okay. You know, it's actually kind of good that for HPC we see this kind of thing, because I remember, you know, like even just the basics of someone needs to launch a GUI application on our systems tends to be a pain in the ass. So, all right. Since we actually started 5 minutes late, we are still on time.
I thought that Mac just worked.
When has that ever happened? Mac works when you.
This isn't Mac. This is Linux on Mac. Let me just change operating systems. It's gonna be okay.
Oh no.
This is where you get to see what all the real pre-compile times are, and nothing hidden, nothing pre-prepared.
Otherwise, you can use my computer if it's like a Google slide or like a PDF. Well, it's a different color this time.
Yeah.
Before that was orange.
Very exciting.
Oh, blimey.
Macintosh is booting. Take some time.
I thought that exactly Linux is what's written in Rust and should just work.
Oh, in Rust?
Yeah,
Oh,
exactly
gotta
Linux.
change
Oh,
my
okay.
password. I just typed in on the screen.
Oh, great. Wait. Okay, this works now. I saw like a desktop 4.
Desktop 4. Okay. Let me just open up Julia and Chrome. Will these work? Do I have to like drag them all?
Unless you change it to
Okay. We're gonna go to mirror. Wow. Okay, this is great.
So you should be good.
And now I just need to open up my slides. I'm just gonna unplug this for a moment. Well, I don't wanna. I already showed my password to the stream. That's no good. Okay, where's So, okay, I'm gonna, oh no. Okay, great. Okay. Hello, hello. Thank you for your patience. Oh, microphone. Hello, hello. Thank you for your patience in navigating those technical difficulties. I'm going to start with a classic demo. I'm going to, does this come out? Yes. Oh, great. Okay, so I'm going to do a little bit of a demo. And this demo is going to be slow because I haven't pre-compiled anything, because I just switched operating systems for the technical stuff. So let's start by using plots. Can we do this? Oh, what's going on here? Okay, whatever, that's fine. So I should just give my talk and then plots will be pre-compiled by the end of it, right? Yeah, okay. So I'm going to get back to this demo later. So benchmarking, oh gosh, what's going on here? Benchmarking has a few different types of use cases. The two primary use cases are interactive benchmarking. So that's like, I've got a piece of code, I'm going to run it, and then I want to make some modification to the code, see if I can get it to run it faster, or maybe change the inputs. You have different inputs run. And that's like at the REPL usually, and quick iterations, and you want quick, accurate results. And then there's automated benchmarking, and that's for regression tests, like it runs in CI. And those have a different prior distribution for what your expectations of the results are, because if you're doing automated benchmarks, you're probably running a bunch of benchmarks on every commit, and so most of the time they're reporting not much. But that's another primary use case of benchmarking. And Chairmarks is a benchmarking utility that primarily focuses on this interactive use. A lot of the design decisions focus there. And it also supports automated stuff just fine, but when I'm designing it, I'm thinking automated, interactive first and automated second. Let's see if, nope, still pre-compiling. Great. So targeting here, I want to support researchers and developers, and anyone else who wants to know how fast things go. But also, researchers are developers, so we can think about developers as the target users. And what do folks want? Whether they're researchers or developers, folks are going to be looking for accuracy. That's getting the right answer. You want to know how fast something is, you want to know exactly how fast it is. You want to get the correct answer. And this is actually an interesting concept of what is the correct answer. It depends on what the benchmarking model is. So I want a semantic model that's accurate, that can be reproducible. So I give you a number, and then if you run a certain piece of code, it'll run in actually that much time, which is trivial for big benchmarks, but for micro benchmarks, it gets tricky. And also with accuracy, and this is probably the biggest thing, if I say X is faster than Y, then X needs to be faster than Y. And that's a little bit tricky in some architectures and some micro benchmarking cases, but again, for the most part, it's doable. And it should be fast to execute. You want benchmark results, you get those benchmark results fast. And simple UI, concise invocation syntax, just for those rapid iteration. And that matters for those interactive uses. So there's this fast versus accurate thing. The longer you run your benchmarks for, the more accurate the results are. To an extent, that's unavoidable. And to that extent, we want to let the user decide how fast to run the benchmarks. But for the most part, we can do both. So there's some key techniques to look at for getting fast and accurate benchmarks. First of all, save all results. Tuning should be, whenever possible, continue to use those results to create the final summary. Now, that's not always possible. For example, if the number of evaluations in the tuning is different than the final summary, it would just confuse things to lump that in. So we wouldn't return all results, but almost all. And then efficient tuning.
tuning in Chairmarks takes 5% of the benchmarking runtime, pretty much always. And that's a number I picked because 5% slowdown is fine, and it gives good, robust results. And then the overseer, that performance, that's like the big loops over all the benchmarking. So it should be efficient, so almost all of the runtime should be spent running the actual code that's being benchmarked, not running code in Chairmarks. I really want to demo this. Great. Okay, so I'm going to start with a little demo of, whoa, look at the time. Isn't that crazy? That's not what time it is at all. So let's see how long it takes to, okay, I'm going to stop talking for a moment to type so I can type with 2 hands. Oh, only 5 minutes left. Wow. Cool. I'm going to skip the demo. And sorry, those technical difficulties really make this talk struggle. So there's no substitute for large sample size. You gotta run your benchmarks for at least a bit of time. Don't need parameter caching because of efficient tuning. So it's just a 5% overhead. How many of you use parameter caching with benchmarks? Yes. Oh, great. Great, no worries, no worries. Okay, we're gonna do a demo. There's actually 25 minutes left, not 5 minutes left. Okay, okay. So I'm gonna say, see how long it takes to load benchmark tools. Okay, 1 second, that's pretty good. And then I'm gonna define a function. F of n will benchmark how long it takes to invert an n by n matrix. So start with an open parentheses, like any good function, benchmark. And from here, let's see, I want to invert a matrix, so write that, and then the setup, have to set up this, so x equals rand, and then have to interpolate these n's. That makes sense because it's evaluating at global scope, so you have to interpolate. Close parentheses dot time. Zoom in a bit. Zoom, zoom, zoom. Okay. That seems right. Okay, and then x, let's say from 20 to 20. That's my sample size. And now I'm gonna see how long it takes to compute all this. And then when I'm done, I'm gonna scatter x and y. And this at time block will only measure the first time. It won't measure the plotting time. Okay, great. So this is benchmark tools chugging away. Oh gosh, ooh, is it seconds? I don't know what that is. Times? Oh yeah, it's times. So I have to, great, times, and then I want the minimum, so I'm gonna do that. Great. Great. Okay, and now let's see. Oh, keyboard shortcuts. Great. Let's do this in Chairmarks. So Julia using plots, and it's gonna be already precompiled, right? Great. At time using Chairmarks. Also takes some time to precompile. Oh, it took longer to precompile because of this package weak dependency. So that's a problem. But 2 seconds is acceptable for precompile time, but I'd like it to be better. And now let's define a similar function, but for Chairmarks, the way we do this is I use @b, so people using short function names, ew, terrible. Short macro names, ew, terrible, don't do that. However, here I am doing that. And the reason is because benchmarking is often a write once, read never thing. And that is so rare in code. Like, how often are you writing code that you're never gonna read? How often do you type code as if you're never gonna read it? I mean, depends on who you are. And so that's my justification for using these short macro names. @be gets you the full benchmark results. @b just gets you the summary, which is minimum. And now we use a pipeline. So think about what we're starting with. We're gonna start with n by n matrix. And then what's next? we're gonna invert that. Great, and we want the time. That's all. And now let's do the same x, and then the same this thing. And this will take some time. Benchmarking is not instant. It takes some time. There we go. Oh, and look, it's a little bit noisy. I wanted to use Maki, but Maki took much longer than Plas to precompile. So this is not ideal, but we can run it again. We can run it a second time, and again, it'll take some time, and it's still noisy. You know, different noise characteristics on different systems. And I think that there's some, yeah, I don't know. Benchmarking is tricky. There's all sorts of things to think about. Maybe it's garbage collection. I'm not prepared to fully analyze all the hardware details that lead to different performance characteristics on the fly on this operating system. I was on the other operating system, but now I'm not, because totally different. Anyway, by the end of the talk, hopefully benchmark tools will have the results, and we can compare the accuracy of benchmark tools and chairmarks. Now, this was not entirely fair, because chairmarks has a default runtime of 1/10 of a second, and benchmarks has a default runtime of 5 seconds. So that's not apples to oranges. Presumably, benchmarks is going to be a little bit more precise, right? We'll see when the numbers come up, and we won't get a great representative sample because I only have time to do the benchmark tools once. But to get a little bit more fair, apples to apples, we can use benchmark tools and ask benchmark tools to give us a runtime of 0.1 seconds, which is chairmark's default. And now this is apples to apples, because we're both asking for 1/10 of a second per trial. And the reason, I should say, I need to justify why I'm using 1/10 of a second default instead of 5 seconds of default. Like, is that just less accurate? That seems bad. The reason is I want speed first, accuracy second. If you're using an iterative development loop, oh look, it only took 20 seconds. So that's good, right? I should do a little bit of math. Length of x, this is the number of samples we're taking, 25 samples. 1/10 of a second per sample should be 2.5 seconds. If we look at chairmarks, 2.6 seconds. There's a little bit of overhead. I'll work on that. Actually, I won't. I'm fine with this overhead. Benchmarks, tools, there's a bit more overhead. So that's why, that's the key thing I'm advertising with chairmarks, is that it gives you the results quickly. And we want fast first, and then, oh, benchmark's finished. It only took a little bit of time, and oh wow. I'm presuming this is the one, right? We can just double check. But this is very good. I think it probably is smoother because it took more samples. And I can run chairmarks for the same amount of time, and then I'll get back to it at the end of the talk and see if it's the same. But let me just scatter x, y. Yeah, so much smoother. So this is that point. You can't get away from, like, if you want really accurate results, you have to run it for a long time. No way around that. Chairmarks is not a silver bullet. Perfect results, long runtime. Also, this is an n of 1 sample because we don't have time to reproduce this. And let's see. And when I was running this on Linux, it still wasn't always perfect. So it would get this half the time and it'd be a little off half the time. I'm gonna run chairmarks with this same runtime. So I'm gonna say seconds is 236.7 seconds per sample. There's 25 samples. And we'll see how that goes. So now I'm going to go back to the talk. No substitute for large sample size. But we do want quick first, and then once you have your hypothesis, you test it and verify it with slow. So slow second. And you can do that by just setting your seconds to be a higher number. Oop, that's not the button I wanted to press. Okay, parameter caching, don't use that. Okay, user interface. This is one departure from benchmarks, the most visible one. One aspect is those function names are different. Another aspect is the return value. I do need to open up a REPL to explain this stuff. So something folks might be familiar with is at btime. Oh gosh, why is this feels bad. There we go. At btime is the like summary version of benchmarks, and it gives you this, but it just prints it. With at b, we've got this result, and then I can say, I can access it. I can say, what's the time, bytes, so on and so forth. So all the results are returned as objects. If you just want to print it, you have to call display. That's the pattern I decided to go with. If you want to show it, you have to call show. If you want to display it, you have to call display. If you want to show it at the REPL, don't do anything because the REPL automatically shows things. Okay, and then the other key characteristic thing that might look interesting is this pipeline syntax. At b, rand 10, sort. So what's going on here is we've got a setup and then a function that's being benchmarked. And this is a pipeline. It's implicit. Each argument is one part of the pipeline. And so this sorting is timed, the rand generation is not. And we've got underscore syntax. This is equivalent. So you can give just a function name, and that will, it assumes it's a function. Or you can give something with an underscore. And if there's an underscore, that would be a parse error. And so instead, I use the macro to parse that as an anonymous function with the underscore as the argument. And with using underscores as anonymous functions, which is a classic tricky thing to get scoping right, here, the scoping is very easy, very straightforward. Like, where does that anonymous function start? The whole block, the whole argument to the macro is a single anonymous function. And so that's where the underscore comes in. That means this is equivalent to this. Those are all the same. And so that lets us do things like sort it in reverse. Oh, it's slower to sort in reverse. That's weird. I should probably get on that. Yeah. And you can have up to 4 things in the pipeline. If you just have 1 thing in the pipeline, it's the thing you're benchmarking. If you have 2 things in the pipeline, then the first thing is setup, and the next thing is the thing you're benchmarking. If you have 3, the first thing's setup, then benchmarking, then teardown. And if you have 4, then it's a one-time initialization, then setup, benchmark, teardown. But for the most part, you just need 1 or 2. Great. So that's the user interface. That's what you'll interact with on a daily basis. And the performance characteristics here are the same as if you ran the body that you're benchmarking in the context that you ran that benchmark call. And so that means if you just put the benchmark call in a function, everything will be fast. If it's in global scope, you might have access to non-constant globals. So just think that you're writing a function and use those same performance characteristics. And that avoids the at eval. There's no interpolation needed, no eval needed. You can do interpolation, and that just creates an anonymous function. And that's kind of complicated to think of on its own, but if you're very familiar with benchmarks tools semantics, you can use interpolation, and it's pretty similar. And you can just continue using that same muscle memory. So that's the basic user interface. There's a little bit of ecosystem developed around it. I made chairmarks extras, which is, I get feature requests for chairmarks, and I'm like, I don't know, this feels dubious, but I guess it's plausible. But I don't actually want to include it in this package, because I like a small, easily maintained package that's got a cohesive, like, only one way to do things. But then People want features, so I put them in chairmarks extras. So if you want at B time, if you want at B allocated, like benchmark tools, they're in chairmarks extras. I have philosophical objections to those in some cases and practical objections in some cases, so I didn't put them in chairmarks, but it's like chairmarks but more stuff. And then pretty chairmarks.jl, which Marco Lombardi made, is chairmarks, but it displays the results in the benchmarks tools output format. I'd like to eventually include histograms in chairmarks, but I don't yet. And so that's, if you like the benchmark tools display format and you want to use the chairmarks backend and front end, you can use pretty chairmarks.jl. That's the gist of it. Let's see if the chairmarks one finished. It did, right? Yes, okay. And we get, look, they're the same. One of these is benchmark tools, one of these is chairmarks. I don't know which is which. And they both have this little lump at 170. That's cool. I wonder what that is. Thank you, 10 minutes left. That's probably real, because it's from 2 different REPL sessions, 2 different benchmarking libraries. So like, that's cool. Something to look into. Why is it slow to invert that matrix? Oh, it's probably just above 128 by 128. That's my guess. Anyway, so they're comparable accuracy if they're running for comparable amounts of time. And if you want to run them fast, chairmarks give you an answer and benchmark tools just doesn't run fast. Yeah, and if you really just want correct answers all the time with high precision, and you don't care about having to wait all the time, benchmark tools is a more robust platform for that. You could also just like hack on a minimum runtime to chairmarks, but I trust the user to ask for the appropriate amount of runtime. Yeah, so that's the prepared part of the talk. Now I'd love to hear questions. I'm sure I didn't adequately explain everything.
So I assume it also collects the whole statistics, right? It just prints the average, I don't know, minimum, I don't know. But please print the statistic as well, even on the short version. I'm not talking about histograms. Histograms may be difficult, but that's the most common issue. Like you say, oh, it took 43 nanoseconds. Now, please show plus minus and how much. Otherwise, people make wrong assumptions from it.
Yeah, thank you, thank you. So use at BE instead of at B, and then you'll get your statistics. I can do at BE 1 plus 1, and we get the statistics. At B just summarizes those into a single number, and the implementation is just summarize at BE. And so at BE is kind of like the baseline, just like at benchmark is the baseline for benchmark tools. I have a few, so first of all, you asked for standard deviation. I have a huge objection to displaying standard deviation because, or I don't know about huge, but I see that misused all the time. You can compute standard deviation of the results. Like I can, what benchmarks tools does, or rolling this back, what chairmarks and benchmarks tools do is there's a bunch of samples, and each sample has a bunch of evaluations. So let me just pull up a diagram. Where's the diagram? There's the diagram. This is the high-level implementation of, or this is the high-level implementation of what the function looks like. You run the evals and time each sample. So each sample has a bunch of evals and it gets one instrumentation. And for like 1 plus 1, the instrumentation, the actual function is very fast, much faster than the instrumentation. So you have to have more than one eval. When displaying statistics like standard deviation, it's common to just compute the standard deviation of all these results, all these times that were displayed. But that's not the standard deviation of the evals. Because there's many evals within one sample. And it's also not the standard deviation of the possible, if you run that benchmark repeatedly, you could get very consistent results, each displaying a high standard deviation. So that standard deviation is like an easy thing to compute, but it doesn't, if you want to know something, it's probably not what that thing's telling you. And in general, statistics on benchmark results are very, very hard because the whole statistics field is primarily focused on independently and identically distributed variables. There's parts of the field that aren't, but it's just so hard to, all the statistics are much harder if we don't have that. And the complexity of computing benchmark statistics, I think is higher than the complexity of making a whole benchmarking library. And so for that reason, I do not display standard deviation. I do display min, max, mean, and median, yeah. And those, they're also statistically suspicious. Minimum you can trust, maximum you can trust, although it isn't what you're looking for. Mean you can absolutely trust. Median you can kind of trust. Yeah, so they're simple and fairly doable. Yeah, you you got me talking about standard deviations. But the answer to your question is at BE.
Thank you.
Any other questions?
So I like chair marks a lot. However, it's not integrated into other packages that depend on some of the format that benchmark tools have. For example, PKG benchmark. Are there any plans to try to be more compatible with those other packages?
Yeah, so some of these packages literally require a benchmark tools.benchmark group as their output. Yeah. And I'm like, come on, like make an interface. I don't want to have to depend on benchmark tools to do this. I made a package called chairmarks for airspeed velocity.jl, and that is just a wrapper on chairmarks that returns benchmark tools.benchmark group results. And that works for airspeed velocity. It might work for this. For PKG benchmarks, I haven't tried it.
Yeah, airspeed velocity has its own words, so.
Yeah.
Yeah.
So the answer is somewhat, and if you have a specific request and you're specific and you like want things to operate, especially if you're willing to do some implementation, like I'm absolutely down to support that, but it's not all present.
Okay. Thanks.
About these two questions. I think you made a very good case for benchmarking is very difficult to do right. And on HPC, it's even more contentious. So do you have do you provide hooks, for example, where I could provide a function that takes an input of the sample values, and then I can go and implement whatever, if let's say I'm a benchmarking expert, I know what metrics I want to look at. And so is there a way for me to provide those to chairmarks?
Yes, absolutely. Hooks are hard. Return values are easy. I return all the data. So at B does not return all data, it summarizes. But at BE, you get all the times, all the data for every sample. And I can show that at BE. Oh gosh, wrong keyboard shortcuts, wrong operating system. So here we go, and I can do x.samples, and those are all the samples. So the first sample was this one, and that it took this long, and it allocated twice for a total of 144 bytes. And I could then look at all of those samples individually, do whatever I want, including basic statistics or fancy stuff. Thanks.
All right. I think we're out of time.
Oh, there's more questions. Tragic.
my name's Ethan Meitz, and I'm a PhD student at Carnegie Mellon University, and I'm here with my co-presenter, David Krasowska, who is a PhD student at Northwestern in computer science. This work was also a collaboration with Wanchan Lee at NVIDIA and Pat McCormick at Los Alamos. And today our presentation is about a library that we've written called QNumeric.jl, whose goal is to make writing distributed, multi-GPU, multi-node programs easy. The high-level goal of our package is to take code that you have written as a user and scale it across whatever system you have access to, whether that be a single CPU, a multi-GPU system, or a supercomputer, without you actually having to change any lines of code at all. So code that runs on a single CPU should also run on multi-GPU as well as your supercomputer. And the kind of motivation for this is that if you're a domain scientist, it's relatively easy to implement your physics in a high-level language like Python, MATLAB, or Julia, but it is much harder to then take that code and scale it across whatever compute resources you have access to. Often the skill sets of physics and high-performance computing are very separate, well, even though these physics codes often scale well on computers. So we're trying to bring these two worlds together, make it so the physicists can use these high-performance tools. So the kind of core type that is enabling all of this magic is called the ND array. This is very similar to a Julia array. We are attempting to implement it so that it is just a drop-in replacement for Julia array, except that it can represent data across multiple devices. The key differences right now between the ND array and a Julia array are that operations are broadcast by default, so even if you don't put the dot operator, it's just going to broadcast your operation. Slices are always views, so we kind of get rid of those extra allocations that are by default in Julia. And then just like with any GPU array, scalar indexing is really bad, but in this case it's extra bad because you also have to go look up which device your data might be on. So it's incredibly slow to do scalar indexing on these arrays. And just kind of a sneak preview to kind of prove to you that this is indeed possible, we've implemented Gray-Scott 2D partial differential equation, and this is the get diff for converting that from a Julia implementation to a QNumeric implementation that runs on multiple GPUs. And you can see the only lines of code we've really changed are just the initialization. So we changed from a Julia array to an ND array, and that was all we had to change to get this running. Looking a little bit deeper at the core technologies that enable this library, we are building off of many years of research by NVIDIA as well as Stanford, who've created the Legion and Realm libraries, and NVIDIA has implemented this Legate framework. This Legate framework, NVIDIA's goal is to implement all of these Python libraries. So their most mature library is called QPyNumeric. It implements the NumPy API, but they also have plans to implement SciPy, Pandas, Sklar, and all of these other libraries that are very common in the Python ecosystem, and then run them on whatever hardware you have access to. And this is nice and all, but this is JuliaCon, and I like writing my research code in Julia. So David and I asked the question, like, wouldn't this be nice to do in Julia? And is there something we can do with Julia that is not actually possible in Python? And David will talk a little bit more about that at the end. And just even more specifically, we are focusing only on this QPyNumeric component. So this is kind of mimicking the NumPy API. So we will have access to things like matrix multiplication, as well as most unary and binary operators. Going a little bit deeper into how Legate is actually working, your program flow might look like this, and this is just using calls from like Python API that you might be familiar with. And the kind of one key thing to note here is that we're mixing all these different libraries. So like you have an HDF5 read, you're using QNumeric to do adds and matrix multiplications. And all this just works because the underlying data structure, the library making all this possible, has the same data format, and that is Legate. So when you run your program like this, each of these functions is implemented as a Legate library. So these are not actually calling the typical Python library. This is a bespoke implementation using the Legate framework, and each of these functions will emit a Legate task, which are then further broken down into smaller parallel tasks that are automatically converted into a DAG by the runtime when this determines your execution and program order. And one important thing here is this is all implicit. The user does not, the end user, the one running this API, does not actually have to tell Legate what the data dependencies are. Legate is just going to figure this out based on how you've written your program. And then the final thing is we take this, or Legate takes this DAG and runs it on whatever your target hardware is. So that was just a little bit of how Legate is working. If you have more questions on how the details of this library work, definitely ask at the end or come up to us afterwards. But now getting into what David and I have done. So the existing software stack that we are building off of looks like this. There's Legate, Legion, and Realm, which are all implemented in C++. And then NVIDIA has gone and implemented a CuPy numeric in C++. So this is taking Legate and implementing things like matrix multiplication, dot products, outer products, all that kind of thing. That is all in C++. And then they have, in typical fashion, bindings to that library, and then the user-facing Python API, which in this case perfectly mimics the NumPy API. We're doing this all in Julia, and our software stack looks like this. So we have C++ bindings directly to Legate, as well as bindings to this CuPy numeric. So we not only have broken out cuNumeric, but we also have access to Legate bindings as well, which will enable us in the future to write libraries in Julia that use these Legate primitives. Most of what we're talking about today is with cuNumeric, except for one slide that David will talk about, where we use Legate to actually run CUDA kernels with the Legate stack. So this is the high-level software stack. But now let's actually get into some results, convince you that this library does in fact work, because it does sound like a little bit of magic. At least I thought so when I first started working on this project. So the first thing we tried to do was Monte Carlo integration. The technical details of this are not that important, but the main point is that this is an embarrassingly parallel problem, so it should scale perfectly. This should be something that's really easy for Legate to handle. The two tasks really that this has to do is generate a bunch of random numbers and then apply some function to all those random numbers and take the mean. So the kind of code looks like this. This is the syntax for our library, and the weak scaling of this for 8 GPUs, which is what we've had access to. We, in the future, would like to scale across multiple nodes, but we didn't have access to those resources for this presentation. But we basically see perfect scaling for both cuNumeric.jl as well as CuPy numeric for this problem. And that's good because this is an easy problem. If we actually look at the throughput for these different kernels, though, we see a little bit of stratification. Specifically, CuPy numeric is a little bit less performant than the Julia wrapper that we've created. And one thing to note, the y-axis here, it's not exactly gigaflops. There's some constant factor that we don't know. And then we also ran CUDA.jl on just one GPU to kind of see the throughput and treat that as our benchmark. So we are getting similar throughput to CUDA.jl and then scaling perfectly as we add GPUs. And we think that this small difference between the Julia and Python libraries is because cuNumeric is directly calling into the C++, whereas CuPy numeric, the Python library, actually has several layers of Python that it's going through before it ends up calling into the C++ library. The next kernel we looked at was matrix multiplication. If we can't do this, we probably shouldn't have come here to talk about, or come to JuliaCon and present our work. The syntax looks like this, and just one caveat. You cannot generate float 32 random numbers at the moment, so technically you have to typecast from float 64, but the syntax we hope to have soon will look like this, and n was not actually 10, it was much bigger than that. So the weak scaling for this, CuPy numeric and cuNumeric.jl, again, scale perfectly, and David wrote a bespoke kernel with CUDA.jl that uses multiple GPUs that also scales fairly well. If we look at the gigaflops for this again, we see that we're basically maxing out the throughput for our GPU. So we scale perfectly, and we're maxing out the memory bandwidth of our GPU. So this is all we could really hope for. So matrix multiplication is working fantastic. And now I'll hand it off to David to talk more about some complicated examples, as well as some cases where cuNumeric did not work as well as we had hoped.
All right. So thank you, Ethan, for the great introduction. So cases where it might not work. We started with Gray-Scott heat diffusion, which is the same git diff that we showed earlier. The issue with this is we ran into this great error right here. We were not able to execute this, right? Why aren't we able to execute this? And it clearly says we're out of memory. And by just enabling a forced garbage collection, we were able to achieve Gray-Scott to run. So each object included in slices are treated as temporary objects within our cuNumeric framework. So why does the Julia garbage collector not collect these objects? So this is a bold claim, but this is what we found that's true, and what other libraries actually do as well, is foreign memory is not automatically garbage collected within the Julia ecosystem. So the garbage collector just sees foreign memory as just a pointer, and it relies, and the base Julia garbage collector relies on the notion of heap heuristics. How much heap saturation do you have present within your program before the garbage collector is invoked, right? So we are using CUDA, we use the profiler, and we look at something that we expect to be 40 megabytes in CUDA.jl. It's a 10 million array element. We take a heap snapshot, and Julia just sees it as 184 bytes of data. And you could clearly see that in the profiler too. So this claim that garbage collection heavily impacts performance here, and you could see by this graph, this is basically, we're trying to force the garbage collection, and we're doing a fixed interval iteration count within our application. So we will iterate through 1, 3, and 6 iterations, and you can see here, as we decrease the frequency, we get better and better performance that converges to QPyNumeric, which we're treating as our baseline. So going back on what AMD GPU and CUDA.jl do, these existing backends really, they know the rough memory footprint the objects will take whenever the object's constructed. So they track all these GPU allocations, they manually invoke, based on some heuristics, the garbage collector, and they have a try-catch block to basically prevent out-of-memory errors like we saw in the pop-up box that I showed earlier. And the issue with our library is we don't know exact sizes at construction of these objects. The Leagate runtime may deduplicate objects or duplicate them in some way based on performance optimizations. And another thing that we can't do is we can't recover from an out-of-memory error within the mapper. So that's not great. So we have to be very conservative if we create automatic heuristics, which is what we did. We have automatic heuristics that enables us to run the Gray-Scott heat diffusion without manually placing the garbage collection call. And you can see here, we do slightly better, and the red line is our QNumeric JL with the new garbage collection heap heuristics versus our old method. On 1 and 2 GPUs, we are performing better and matching what QPyNumeric does. However, when we scale for some reason, which we're looking into future work, we don't get exactly what we need to. So this is great that we have an automated way of running a garbage collector, but the issue here is we just don't scale as well as we need to. So another aspect is you may have seen that there's a dotted line of floating point 32 theoretical performance on this Gray-Scott heat diffusion application. We're pretty far from it. And we started to look into this, like why are we so bad relative to the peak theoretical performance? So we decided to rewrite a test application of the same application in a Julia library, implicit global JL. This is a stencil-based PDE solver that runs on multi-node NVIDIA and AMD GPUs with minimal code changes. And their library performs extremely well. And so we started analyzing this. And one of the big things that our framework doesn't do is kernel task fusion. There's a high degree of overhead in the sense that if you launch multiple operators, operator by operator, every single one of those operators has overhead. So this is work done by the Leagate team at ASPLOS 2025, and they basically got a 1.8x speed up on average throughout a diverse set of applications and up to 10x. So that 10x is a huge difference for just doing kernel fusion, and that's roughly the same gap, that performance gap that we have. It's about a 10x difference. So this led us into what if we do some sort of fusion? Of course, that entire back-end support is a lot of work, so we decided to start with just utilizing CUDA.jl and write custom kernels and see how that registers and weak scales with our runtime. So the ability to register custom CUDA JL kernels with our runtime, basically this is a normal CUDA JL kernel without any modification. You could initialize our CUDA numeric arrays, so just initializing the data, and then you could launch and compile this is a kernel add, so it's a very simple thing. The thing is, whenever you launch, you have to specify inputs and outputs. That's just a part of our heuristics. In order to build the DAG implicitly, we need to figure out what the inputs and what the outputs are. In the future, we'll probably do some sort of LLVM pass in order to automate this potentially. I don't want to promise, but it's great. You could have a custom CUDA JL program and it works with our framework. There are some caveats, but I'll get into this example. So this is a Grayscott heat diffusion, but a one-dimensional example, and it's just a subset of the kernels within that larger application. And you can see the syntax here is just the kernel, and we achieved, like CUDA JL, they also support their own custom kernels, and they have an operator by operator syntax. So our library does that, and you could see the difference. The blue is the fused kernels that I was just presenting, and then the red was the prior when you unfuse, doing operator by operator. There's a substantial difference in the sense of you could get a performance benefit by fusing kernels, and that's what we saw with the prior work with the League 8 team. And that's also what you see with the CUDA JL library. You could get a performance benefit by fusing kernels. So to summarize this work, operator invocation overhead really just limits performance scalability. And we have ongoing, like this is an ongoing work. As you could tell, I did 1D instead of our 2D example. Multi-dimensional support is not prevalent yet within the custom CUDA registration. So there's ongoing backend enhancements to support the multi-dimensional cases and also multi-GPU execution. The reason we have a bar graph is this is only on a single GPU, unfortunately, right now. But by the time we release this package to the public, this should be able to scale multiple GPUs. And then you could tell that CUDA JL versus our package, CUDA JL is performing better on a single GPU, so why use our package, right? The backend overhead is amortized as you increase the number of GPUs. We're doing the same data dependency analysis that enables the multi-GPU execution. So you could get that for free once we get that supported. So that same backend cost will be there even if you scale across multiple GPUs, so it gets amortized. So some of our conclusions, you could do minimal code changes to your Julia CPU code, and it runs across multiple GPUs, multiple nodes, and you could see we get good weak scaling for some of the examples we showed. The ability to register custom CUDA kernels with the CUDA JL framework backend. And then our next support steps is basically supporting a wider range of custom CUDA kernels. Like I mentioned, there's some caveats. However, we're still working on towards getting everything supported. Hopefully by like September, we want a beta release. And another thing we want to do is improve robustness of our application. Right now, just installing things are pretty messy. So like as a user at JuliaCon, you might run into some problems trying to install our application. And then another thing we want to do is enhance the integration with the Julia runtime and abstraction interface. At the current moment, there is a huge problem, I would say, is we're treating this library as a C++ FFI interface. We're just calling in to C++ mainly. As you could tell with one of the results that Ethan presented with Monte Carlo integration, we were performing better than the Python interface. The Python interface has more integration, and we'd like to do more integration to use some of the Julia runtime heuristics and stuff like that. So that would be a future work to explore. How do we integrate it more with Julia? Another thing, multi-node systems. All our results have been single node. And the goal is to test this. We haven't tested it yet for multi-node support. In theory, our entire software stack should just automatically make this work. However, of course, nothing works as you hope. And then, yeah, with the garbage collection heuristics, the goal is to make that, as you could tell, with like 4 GPUs and 8 GPUs, it was falling off. That's not great. So we want to fix these GC heuristics. And some of the things, in order to do this, we would need better information about the programs when things get out of scope, that kind of thing. The issue is we're relying on, the runtime gets notified of an object's like lifetime based on our deconstructor calls within garbage collection. So having better GC heuristics will reduce false dependencies of objects within our runtime. So that will enable you not to run out of memory. That's a huge thing. And then automatic kernel fusion is the experimental work that I was talking about, the Leagate team. And that would be really cool to implement in the back end. And then operator by operator automated kernel fusion, then just a general abstract array Q-numeric JL program will just magically work. And you'll have a better scaling that we see, and the performance gap will be mitigated. So yeah, we're looking for a September beta release. Hopefully we could get there. I think we're on good track. There's a lot of features that we're still just developing and engineering through this. I believe we started this project late December. Yeah, late December is when we started this. And it's made fast progress. And I'm excited to hear feedback from this community about this project. And I'd like I mentioned, to integrate more with the Julia language runtime stack, because right now we're treating it more like an FFI interface with minimal Julia code. So how can we integrate and tightly couple the Julia runtime stack with our runtime stack? So thanks to our collaborators at NVIDIA and also Los Alamos that made this, and then thank you for making the introduction, Ethan. Does anybody have questions?
Awesome talk. As someone working on Dagger.jl, which is a related library, I find the ability to kind of implement your own parallel algorithms as a directed acyclic graph very powerful. That's what we're doing with Dagger. I'm not sure if I saw it in the presentation, but do you have any examples of how you actually do that with Legit.jl, or do you have that integration, and is there like kind of a plan to make that like a first-class interface?
Yeah, right now, like we don't have that as a first-class interface within Leagate.jl. Do we have plans for that? I would say so, but it's engineering effort at the moment.
Yeah, because like Legate.jl is a separate library from Q-numeric.jl right now, and we basically just implemented the things in Legate that we needed to launch the custom CUDA kernels. But I do think it would be really cool if you were able to write Legate applications, Legate libraries in Julia using Legate.jl. That's just more developer time, but it is definitely possible.
Yeah, because basically how Legate works is you as a, let's say you're a library developer, right? For every operator that you want to support within your library framework, you just register that task to the Legate runtime. You register also what the dependencies for that specific task are. So you have a notion of what are the dependencies, and you register that task with the runtime, and runtime knows about it. It knows how to schedule it. It knows what the dependencies are. But that's all internal C++ code within the Legate runtime.
Great talk. For anybody who's been in the computer science community for a while, you know there's nothing new under the sun. That's a principle of computer science. 25 years ago, we had a parallel MATLAB thing going on, and we learned very quickly for the need for kernel fusion because we implemented one kernel at a time, and it killed us. So that's an old notion.
Operator invocation overhead is killing us in
It's
that
the
example.
same story.
Yeah.
A challenge that I want to put out is, and this is not how one starts, but I'm not sure anyone ever gets there, is, once you've got a small list of things you can do, matrix multiply, parallel Monte Carlo, dot products, maybe there's a list of 10 basic things. You get those, and then what comes next? I mean, I've always wanted to see a world where people who write serial code, just to do anything, not Grace Scott, but whatever, the 99.9% of things that people really do, how do you get parallelism there? And I'm not expecting an answer, but I'd love for you to think about it.
Yeah, I mean, the overall goal of Leagate is implicit parallelism, right? Extracting out all independent partitions within any of your tasking operations. However, like you mentioned, it could be any arbitrary code that might not have any parallelism characteristics. And how do you extract that out, right? That's a good question. I don't have a good answer for. If there's not parallelism that exists in the independent task graph, it's yeah.
Yeah, I had two quick questions. So one is, so it's building on an NVIDIA project. Have you also looked at how performance is on the CPU compared to how you would usually write CPU code? And does it run on AMD GPUs at all? And then the other question I had for the GC part, did you look at how the Python side solves that?
Yeah, so the first question, the CPU thing, we have not benchmarked it, but this library and the whole Leagate stack also works for CPU code. We were more interested in the GPU stuff, though. What was the second question again?
Python ref counting. So the reason Python doesn't have this problem, and they didn't have to implement any specialized heap heuristics for CuPy numeric, is because Python has a ref counter for external memory references, right? Whenever something's out of a scope or anything like that, then the deconstructor is called because there's no references to it, right? The Julia garbage collector is, I guess it's a mark and sweep algorithm based on heap heuristics and heap saturation. Because our external memory references don't saturate the heap at all, right? Everything's just an 8-byte pointer, no matter if it's 20 terabytes or 2 megabytes, whatever it is, Julia doesn't see any of it. And that goes into my point of having more tightly coupled integration for stuff like this, and includes the registration of the ability to notify Julia of the sizes of external memory references. That would be potentially useful for libraries like AMD GPU, CUDA-JL, and our library, because and Dagger.
The second question was AMD support, right? So this does not support AMD right now. As you can imagine, NVIDIA is not super interested in doing that. They're not going to stop you, however. So Legion and Realm are completely agnostic. It would just require someone to go and implement these things for AMD. And I think there is some things in Leagate that are specific to NVIDIA that David can maybe talk about.
Yeah, so right now the entire Leagate stack is just NVIDIA specific. So what Leagate does versus what Legion is, so Legion is the entire heterogeneous scheduler, and it requires a notion of a user writing a mapper, right? Leagate automatically writes a mapper for the different operators and data dependencies. It has its own heuristics and stuff like that. But those heuristics are specific to NVIDIA GPU devices to do its partitioning in an optimal way, and especially the CuPy numeric and stuff like that. Behind the scenes, it's all just NVIDIA specialized kernels to implement all these different operators. So in theory, this could work, especially the shortest path to getting this working with multiple devices is if the CUDA-JL registration using AMD GPU registration or something like that. But you would have to create custom mapper heuristics in order to get this support within Leagate. And that will enable different types of GPUs. But NVIDIA does not want to support this, unfortunately.
So technically possible, but a lot of developer time.
Yeah, and there's no support for it.
All right, so since we are very close to lunch, and most of my questions have already been answered, I want to thank the speakers again, and we will reconvene at 1:30.
Hey, no, what time? We don't start till 10 tomorrow. In here, what time we're scheduled to come in at 8 though. I don't know, but regardless, what room are you in? I'll come up to your room in the morning.
I am in 323. 323. I'll just come up to your room. Yeah, that might be. I mean, it wasn't too bad after just the first speaker started. There's like four. There's no AC in the room, so there's like four huge windows, like this big each. There's four of them, so they're like making a bunch of noise and stuff. I'll bring it anyway.
was another room. I was in the other place.
Oh. Yeah. And then tomorrow we'll do it again.
It said on the website everything is in the reference hall. Said in the Julia website.
So it looks like after you, there's actually a break. So we can like, we're not completely.
Okay. Oh.
We don't have a hard end. Maybe people might, actually there's a break in everyone. Like a coffee break again.
Do you see it? Because I don't
No, no, it's they're static.
Still plug your HDMI, plug it back in.
That's what the first thing you said.
Are you running Windows OS?
No.
Okay, that could be a problem. That could be a problem. So what was it the last one?
I thought it was in the other room.
It's easy. Yeah, it's on the shelf or something. Are you gonna sit while you present? Or are you
No,
gonna
no,
stand?
no,
You're
no,
gonna stand
no.
up? What resolution are you uploading? Under display? You're not using Windows, you're using
Oh wait, something's happened. There's a mouse.
Okay, that's good. Must have detected it. There it goes. Okay, you're good. Maybe we'll just be on mirror display. Display preferences. Which you are right now, so you're good.
But it's not doing it. You kind of hit it. Kind of move the window.
Yeah, but it's mirror. It's showing the same thing that's on your screen, so it's not. You're not in like something.
Yeah.
So if you just go full screen with that,
But another doesn't know how.
you can't grab it and drag it over.
No.
Go to.
Okay, now.
Yes. You were, yep. That's it, yep. That's it.
You see the, yeah? Okay. All right. Hello, everyone. Sorry for the little delay. I thought it was in the other room. Everything was supposed to be there, I thought. Anyway, so yeah, so welcome to my talk on generating architecture agnostic performance tests from functional unit tests. So I will present this talk, but the hard work was done by Daniel Sergio Vega Rodriguez. So he was a master student at USI, Università della Svizzera Italiana, and I supervised his thesis together with Professor Olaf Schenk and Timostonis Pasadakis. And yeah, so that is really the development of the package I will show is really his work. I have been contributing by it was my idea to do that package and to think how to do that, etc. But he did the hard work. So I will talk about motivation, fundamentals, package design, how to use this package called perftest.jl, the results and conclusions. So first, motivation. There are HPC examples that show that it would be really good to have a unit testing, unit performance testing framework. So to test performance at unit level, just like we do it for functional tests. And so actually the very beginning was exactly this implicit global grid that I've been developing at CACS. And so this package does a halo exchange, like it says here. And to do that, there are like different layers of abstraction. And in order to copy the halo with very low-level functions, and then on top of that we have more abstractions and so on. And so in order to make sure that at every level of abstractions we don't lose any performance, I thought, well, I should test that. And I want to be sure every time when I have a new version that I don't lose any performance, right? And to test that every time is difficult. And I don't want to go to dig in every time to see where now I lost performance. And so I actually started to do like an ad hoc performance test. I copied the whole performance, the whole unit test suite, or less not the whole, but a part of it, and transformed them into performance tests. Then afterwards, the problem was that to maintain this was a lot of work, right? And so that's why I thought actually that would be a good student project to do that. And then there is a second real-world problem that we looked at, that is Paradiso.jl. And so, sorry, just one. It's a bit far away, so difficult. Okay. So there is a second use case that we looked at, the Paradiso.jl. So it's a sparse linear solvers that are which are key components in many numerical computing algorithms. And so input matrices can have very different sparsity structures given the field of origin. Now imagine a user who installs Paradiso as a dependency for the project, then the user wants to check that the package is performing as expected before using it. And so with a framework that you can just run that checks that the performance is fine, not only the functional tests succeed, that's really good. And we see afterwards, in the end, how we really could test that and the difference it made. Yeah, so in summary, the motivation is to facilitate the development of unit performance tests for HPC applications. And in addition, we want to do that in an architecture agnostic fashion, such that these tests can run on different machines, that you don't have to do new tests for each machine. And so we do a Julia package to implement this concept, this idea. So the fundamentals of this idea. Well, first, performance testing, you're surely aware about that. We have different metrics, right? Time, flops, bandwidth, iterations per second. And while in functional testing, it's obvious. You have an expectation for a result, and you check against that. In performance test is not so obvious, and so we deal a bit with that. And besides that, so this is not only new in the Julia world, this is really something new in general. If you search in literature, you don't find anything like that. Now, we want to do architecture agnostic performance testing, as I say, and so it means that we will normalize the values from the metric, for example, flops or bandwidth, throughput, memory throughput, or effective memory throughput. We will normalize that. Check it against a reference to see, for example, okay, we got 80% of the expected performance. And so we want to do declarative performance testing. So we want to say, we don't want to say in detail how to do it every time, but just to say what we want to test and what methodology to use. And you will see later what methodology means exactly. And so here you can see an example of how it looks, this code, right? So you see we have a test set, just like in functional tests. Then we create some data, we initialize some data. Then we do some computation here, the inner product. And you see we put this perf test macro in front of it to make sure that now this computation will be checked for performance. And just the 2 lines above showed what we will be checking against. So we will check the maximum time against a certain value that you define here, function of the number n, and the median time. And so we check that these two conditions will be checked every time. Now, the performance testing methodologies that I mentioned. So we have either simple regression testing, just to check, did it go down, the performance, compared to the last time we ran it? But we also have testing with effective memory throughput or roofline modeling. So we can check that the effective memory throughput, which is basically when you consider only what has to absolutely minimally travel from your main memory or global memory to the processor and back. And you don't consider any redundant reads or unnecessary reads or writes. So that's the effective memory throughput. And the roofline model, surely everybody's familiar with. You see in the bottom right how that looks like, right? You have this roof. there is a corner, and so the first when it goes up the roof, it's memory bound, and afterwards it's flop bound. Compute bound, and so and yeah, I mean on the y-axis you have the flops, and on the x-axis the operational intensity. And so now this package can then draw that based on what you obtain, based on the results. And you will see this in the results. So the design of this package so why Julia? Well, I guess here I don't need to convince anybody why, but let's just say metaprogramming, of course, is very powerful for this. The ecosystem that we have, also including that we have already this test suite for functional tests. We have benchmark tools, etc., etc. And we have a growing HPC and scientific community. Now, here's a little outline of how that works. And so you can see that there is there in violet you see test set, right? And inside, in blue, we have local initialization. So in each little test set, you have some initialization. You initialize some arrays or whatever. Afterwards, you have computation, and then some functional tests, and local finalization. And so what's the key here? The key is that in functional tests and in performance tests, we have the same essential structure. We initialize something, we compute something, and we check if either our performance or our results correspond to expected values. And so we make use of that in this package in order to have both in one single file. Let me check. Yeah. Then, so then it goes through this transformer, through this package that uses macro tools in order to transform this initial code with unit tests and performance tests to transform this in some actual code that can then do this testing automatically using benchmark tools, etc. So it uses this benchmark groups feature from benchmark tools. It uses advanced features from benchmark tools. And you see, so when you generate the functional test here, when you generate the performance test, the functional tests are going to be removed, right? So such that you can run the functional tests independently from the performance test and vice versa. This package implements a new type of test set that holds extra features meant for performance testing. And the test sets of the recipe file are transformed into this new implementation. Now, how to use it? So here's really the essence how that works. You have some Julia project, you have some unit tests, and So you add this perf test macro in front of what you want to test, right here. Before that, you do a certain configuration if you want, and afterwards you have the unit tests. And it goes then either you generate the performance test or the unit tests, and you're done. Now, how to show that, to point it out a little bit better, you can see here really well that the result from the functional test is the same as what you computed here in the performance test computation. Now, there is a lot of possibility to customize. So you can define new metrics, and you can use some special symbols here, like this here, median time, in order to define very quickly your metric that you want to use. If you want to not to use effective memory throughput or roofline. Then, of course, you have some documentation. And now let's look at the results. So first for the implicit global grid case. So here we measured the effective memory throughput. And the unit, the particular unit that we chose here to show for the example that was tested was the transfer from the received halo to the local domain array. So this means the following. So what is obtained there in the blue, in the halo, and then what is obtained there is obtained in a buffer first, and it has to be moved there. This buffer can also be on the host, right? Doesn't matter. But so we have CPU tests, GPU tests. So meaning that in the GPU case, it's when you have a problem on that you solve on the GPU, and so it will test the performance against the expected values, which are obtained with some benchmark, in this case the stream benchmark for CPU, or something similar for GPU. Or actually, sorry, for GPU, it's actually the bandwidth between the GPU and the host, right? So whichever connection that was, PCI Express or something like that. And so we get there the theoretical value, and next to it, you see, measured is what we obtained with the package, and you see we got almost 100% everywhere, so it's good, right? But if at some point it would be lower, then it will flag that. Okay, you got down to 80%, you need to do something. And so actually here we had 91% in one case there. So there actually we need to go check what's happening, if that's not improvable or if that could be better. Then for the linear solver, with paradiso.jl. So this example features a unit test on the factorization step, and that's the most computationally demanding. And so we include here two input sources, diffusion matrices and real-world matrices. So these real-world matrices were really extracted from real-world data somewhere to have something very meaningful. It's from civil engineering or material science. And now here's something really interesting that brings us, that shows another interest besides the development of the code, besides that it helps during development. It shows that when you use, for example, this Paradiso library, you can, when you want to just use it and run it, that you can first check after installation that your installation was done in a good way, right? And so, because here we tested with two different Blazor versions, and with one we'll get much better results than with the other. And so when you have, so this performance test would then also show you, oh, you did something not well in your installation, right? And so here you see the results. You can see always on top here, the points are the results with Intel Blaz, and on the bottom are the results with the other one. And the Intel is outperforming very much by like, factor 3 or 4 or so, depending on where you are, where you look at. And then so the next thing is that as a developer, you decide where you want to set the threshold, right? Where you want to say it will flag a regression or just that it's not fine. And so this threshold is this blue line here. And actually you can also do this threshold that it really follows the roof line. That it's not just one value, but that it follows the roof line, that you say you want to have 80% of the roof line or so. Then as a little bonus, we have the Bencher platform that we use, and we'll show you how that looks like. So this is a CI/CD performance regression platform. And so there, usually they just check if before the last time the performance was worse, right? Or let's say the runtime was worse, and that's it. But we can also put all our data in there. And so you can then compare between Git branches and commits, between machines, between software units, between metrics. And it supports also other languages like C, Rust, or Python. And so perf-test.jl offers a Julia adapter in order to put that there. And now here on the right you see the example. You see here 3 lines, 3 different colors. And here in the vertical you have the different versions of a certain branch. And so we compare here between different versions. And you see the blue and the red line, they're flat. So it means we have no change. So that's usually good, right? Because what we measure here is the median time. But this one here goes up very much. So we see, okay, with our last changes that we did, we have now our solver takes much more time or whatever it is. So with that, I get to the conclusions. So the performance regression unit testing is a largely unexplored practice, and I believe it really holds very significant potential. I believe it can really improve how we can develop our codes, and we can save time in the end. It helps both to maintain it, but also the development itself, that you are faster when you always see how things work out with respect to performance. And as I showed also, besides development also, it allows you to quickly check if an installation was done correctly, if you have the right dependencies used, etc. Voila, and the effectiveness of the package was demonstrated in 2 real-world examples. And we have a little paper here submitted called Generating Architecture-Agnostic Performance Tests from Functional Unit Tests. Future work is to integrate performance counter use, for example, liquid, mature the bencher work there that I showed before, and to increase extensibility and configurability. But yeah, so this is really an ongoing project. The student that I told you is now doing a PhD, continuing this work. And so yeah, this is really something being worked on very hard daily. All right, with that I conclude. Thank you very much.
One thing that I noticed, I was wondering about a little bit, was there's, in the perf compare macro, there's typically a constant. How does one choose that constant? Like, you know, do you do it empirically? And if I took, you know, some of this code and ran it on a Raspberry Pi, for instance, would the test pass there, or would it depend upon the hardware architecture? Like, how do you reconcile those things?
You mean how to define the threshold?
So like there's like a perf compare where like you compare the, I can't remember if it's the median or the mean to like a function, like 0.00005 times n. How do you, where does that number come from?
Yeah, well, that's maybe a bit a contrived example. You should rather think about, you choose a metric, like memory throughput, right? And you say, if I am at 90% of the peak performance that I can get on whichever machine, I will say I'm satisfied. I don't want it to flag, right? If it's below, it will flag. You just say it's not good. And so you choose yourself, like what's the percentage of the peak performance of whatever metric, and that's it. Was that clear?
So is that dependent upon your machine, that peak performance thing? It like takes some like scaling based on the machine? Is that what that means?
Ah, okay, let me show the other slide again. So here, for example, where it says benchmark. So this is benchmarked using the stream benchmark, right, on the top. And below it is with a tool from NVIDIA to check what is the best speed you can have between CPU and GPU to move data. So these are benchmarks that you can find or just create yourself. And then this will give you the peak performance. And then afterwards, you set the threshold that you say I need to achieve with respect to this peak performance.
Makes sense. All right, thank you.
Do you keep do you have like an archive of these machine-specific benchmarks, or does the user provide them in like a preference or something like that?
Well, so far there is effective. Well, this is the stream benchmark. There is this other benchmark that I just mentioned before. And that's for flops. For flops, it uses BLAS, matrix-matrix multiplication. I think that's it for the moment. But you could also choose yourself a benchmark. But I guess one can extend that, yeah.
What I mean is, like, does the package have like a list, like if I'm on an A100, I already know the numbers for that processor, or does the user just stream themselves and put the numbers in like some global setting somewhere?
Yeah, you can also put the numbers if you know them, yeah.
Okay, right.
But let's say the advantage of running a benchmark is that you don't need to do anything, right? You don't need to have exactly a list for A100, for V100, for H100, et cetera, et cetera.
So when I was listening to this, I originally understood this as that this process you have, it will automatically, by default, it'll automatically run these benchmark programs for your machine. Did I understand that correctly, or?
That it will automatically run the benchmarks? Yes.
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 Yeah, okay, yeah. That's what I thought you were saying at first, but then I think some people were hearing it. The alternative interpretation was that you had to implement you had to run them yourself and plug them in. And so I was like trying to figure out which one it was.
Yeah, so there are a couple of benchmarks, like I said, for flops, for memory throughput, for data movement between CPU and GPU. But if you need something else, then you either need to plug in the values directly if you know them, or create your own benchmark.
Thanks.
One follow-up. Have you looked at MPI yet?
You can also use that with MPI, yeah. You just need to make sure that after the computation you have synchronization. You need to add a barrier.
What I was thinking more like is we could just take the MPI.jl's test suite and then run them nightly, and then whenever the system software gets updated, we can get a, I'm thinking like reframe basically, but better. I don't know if you thought about that.
To include it in MPI, you mean?
No, what I mean is make it part of the system checkout after an upgrade.
Yeah.
So
in MPI.jl.
Yeah, so we could just take all the MPI.jl tests. So what we currently do is we use reframe and the OSU MPI benchmarks. But then there's a lot of, I guess it's a little bit slower, but probably okay. And I'm thinking this might be a much nicer way of systematizing that.
Yeah,
I wanted to get your thoughts on that.
Yeah, so basically, when as a supercomputing center, before you return the machine to the users, you want to check, is the machine running fine, right? And so you said you use reframe until now, where you have to create little checks all the time, and you check only, what you really by hand with hard work implemented. But this way you could really just, if this is systematically put into MPI.jl, you could just run that as well in order to check if the system is healthy, right? Yeah, absolutely.
Any last questions? Let's thank the speaker one more time. I think there's a keynote now that we're a little late to. I'm sorry. We'll reconvene at 3.
Yeah.
And it's just sort of based on at some point we just did some averages and then we
That's a cool idea, really. Yeah? Let me know how that goes, and you can also,
I'll let you know.
Collaborate in that. The student is interested in anything.
So is this Sergio that's working in Barcelona now?
Sorry?
Is this Sergio that's working in Barcelona?
No. He's doing a PhD in Switzerland at the UC. Okay.
So he's still working with you?
Not directly. He did with me the master's thesis and and an internship, and now he's doing a PhD with a professor at UC, which is right next to the CSCS. You know, so.
Okay. Cool. No, I'll give that a try. I'll let you know how it goes.
I don't know if you know how it works.
no problem. Yeah.
Nice. You had a different tablet before, right? No. Okay. I was thinking there was like another fun title that someone actually turned into a boring title. Not that this is boring. Because is that the title's always fun. Oh. Also, what's this? Break it down. I like it. Oh, yeah. Send it to some commits and I'll print you one. All right. I'll mail it to Germany. I'm not gonna. California, that's right.
I'll mail it to Germany. I'll mail it to Germany and then you can fetch it.
They have to pay me another money in your terms.
You're not here in LA. I'm gonna be in LA in August. You can always come down to LA and look at what you want. But you gotta send the commits first.
Yeah. Yeah, maybe something. Just to,
Yeah,
yeah.
some stuff about that one here.
Oh, excellent.
Yeah.
Is there also updates about distributed links?
Briefly, but I'm leaving that to James.
Oh, when is James?
Not really. There's, I think he's 2 talks.
Oh, yes. Oh, actually, so this one is also distributed, such distributed much more.
I think
Thanks for setting it up.
yeah, of course. And then are you our host?
Yes.
Okay.
Yeah.
Where you sit?
Yeah.
Okay. And you're gonna let us know.
I have. I have 10 minutes, 5 minutes.
And what is it relative to?
The total stop.
So the whole 30 minutes?
If you decide not to take questions, then you can talk.
Okay, so 10 minutes, let's like start wrapping up, getting to like our last 3 or 4 slides, and 5 minutes, let's try to cut so we have time for questions.
But otherwise, I guess, I mean, it's good to have questions.
But it's okay. People will find us later.
Yes. Yeah, that's, I'm not, at least I'm not thinking it different way. Other people sometimes are feeling like they are something. So that's a question. And then you want to come up with silence.
I also made the slide.
Yeah, I don't have any questions. Let's confirm this one. Very good. Just use this real time.
It was good. And just make sure that one of us actually watches something.
Oh yeah, I will hold it up until someone actually.
Cool.
Yeah. No,
You can wait too.
Look, the reason why I sit here is it's actually pretty obvious. You will see this. Right, so I had a
When I was
right. Yeah. Yeah, I guess I just had the last All right, folks, I think
we can start on time. So welcome to the afternoon session. And we're starting with, is it both of you presenting? So Julian and Felipe talking about Dagger. So.
All right. So what we're going to talk about in this talk is all the cool new things that we've been developing in Dagger over the past year since JuliaCon 2024. So we've been putting together a lot of stuff, but we should acknowledge the people who've actually helped make this happen. Myself and Felipe, as well as the many people on this list and some not mentioned. You'll see their icons here. They will be listed on the slides in the top right corner for when someone contributed a certain feature or helped push something through. So real quick, what is Dagger? Maybe you've come to this session and you have no idea what Dagger is. That's okay. So Dagger is essentially a pure Julia runtime and scheduler and essentially an implementation of automatic parallelism. And we're going to see some instances of that automatic parallelism in a little bit. Additionally, Dagger provides a number of abstractions for multi-threading, distributed computing, including with distributed.jl and MPI, and targets all of the GPUs available into the Julia ecosystem through these abstractions. Additionally, Dagger provides a built-in partitioned array called a D-array, and algorithms which run on top of these D-arrays in a highly parallel manner using these previously mentioned multi-threaded, distributed, multi-GPU capabilities. And additionally, there's a fancy framework that we have called DataDeps, which allows you to write these highly parallel algorithms if you need to write something that's not yet implemented.
So now that you know what Dagger is, what can it really do? Well, it's proposed to be, as Julia mentioned, an automatically parallel system. So if you want to use MPI, it should be as simple as declaring the acceleration. As you can see on the second line there, you just declare your GPU arrays as you would in a GPU implementation. And then you would set your options for running the following algorithm you're about to implement with options call. You distribute this array or this many arrays to one, many, or a cluster of GPUs. You do a really simple add stencil call with the macro you're seeing, and it works as a broadcast would in this example. However, you can build any stencil algorithm you want with padding, with wrapping, and your boundary conditions for a convolution.
And also, real quick, DA, DB, and DC in this example are D arrays that where the partitions live on multiple GPUs on multiple MPI ranks simultaneously. And so the stencil up here is then running on multiple GPUs across multiple ranks. Just wanted to make that clear. So, okay. One of the key things that people have brought up again and again about Dagger is that there's a lot of overhead. Dagger has a lot of task overhead. Dagger makes a lot of allocations when you use it. And that has really impeded the performance of many calculations. So what we've done over the past year and a half is really try to push down Dagger's overhead into manageable levels. And so we were able to succeed at that. So through quite a lot of just hard software engineering work and improving type stability, memoization, caching, all sorts of tricks, we were able to get Dagger's overhead down by about 2 to 4x for quite a lot of problems, especially for where the problem is dominated by task overhead, where you're working with lots of very small elements and thus having many tasks. So in this example of doing a matrix multiply, we went from 5.3 seconds on the prior Dagger master down to 1.6 seconds with quite a large drop in lock conflicts of almost 10 times. And this is now living on master on Dagger 0.19. So additionally, something that we've been working on is improving GPU support. So Previously, anyone who's used Dagger with GPUs knows that we've had the Dagger GPU package. It was kind of annoying that we had to have Dagger GPU. It's like, why not just have Dagger and CUDA and you're done via package extensions? Well, that's what we did. So now if you want to use GPUs and Dagger together, you just say using Dagger, using CUDA, and you're done. All of the code that you need is loaded. We've also added a bunch of tests running with every single commit pushed to the Dagger repository that run across all of the supported GPU platforms, which for reference are CUDA, AMD GPU, one API, Metal, and OpenCL. And everything is going to be tested on all of these backends in the near future. Additionally, we have good tested support for linear algebra and for stencils that we're pushing through now, working out a few little details, and all of this should support multi-GPU as well. So taking a slightly different tact, there's quite a lot of applications that are best expressed as a continuous set of operations, or a set of operations being done on a continuous stream of data. So this is super common in the corporate world, using things like, not Hadoop, but all the various AWS services and stuff. People are, Kafka, that's the one I'm thinking of, where you have just a stream of data coming in order, and you just want to run the same operation on this data again and again and again, potentially infinitely. So Dagger now has support for this, thanks to our Google Summer of Code project last year. We implemented a streaming interface where, in this example above, we're creating a channel, filling it with values, and then with just basically 3 actual lines, really 4 lines, we are taking values from a channel, adding 1 to each value, and then printing them. And that channel can be infinitely filled with values, and this will just keep running, no problem. 4 lines of code. Together with this work, as part of that same Google Summer of Code project, we also implemented something that's called cancellation. People often know this as like interrupts or Control-C as kind of a related variant. And I have a talk about this tomorrow that goes into more depth, but basically what happens if your code is just running off the rails and you just want to stop it? Dagger now provides a mechanism called dagger.cancel, which allows you to cancel or stop Dagger tasks and allow other Dagger tasks to take their place and run. And it also lets you, if you somehow manage to break the scheduler and you need to restart it, but you don't want to restart your Julia session, there's also a variant that lets you do that quite easily. I use this for development all the time. It works awesome.
So as Julia mentioned, we have the data depths capability. Integrated within that, with the framework we have in Dagger, we can quite easily enable, and we could do that, we could quite easily enable MPI, communication between tasks or between ranks, as you may know them in MPI. And you don't need to think about MPI whatsoever. You just build your data depths code as we showed in the first slide. You call a line, dagger.accelerate bang, and you pass in the symbol of MPI. And all the collectives and P2P communication is done by us by default. We are developing a GSOC project with Jan, and he is developing the no-copy transfer of data between sparse arrays and dense arrays. So this is a performance improvement on our current MPI implementation, which we are almost ready to ship.
And there's a talk about this in actually a few minutes, 20 or 30 minutes in the same room about this topic. But so everybody here who has used distributed.jl knows that distributed.jl has various problems. For one thing, multi-threading support is not there. And that's kind of crazy when you want to be able to use Dagger with both multiple threads and distributed. You want to start, say, a Julia worker on each node, but then on each node you want to use multi-threading. Distributed.jl will just explode in spectacular ways if you try to do this. So what we've decided to do, now that there's this cool library called distributednext.jl, which fixes many of the issues that distributed.jl has, we have a very easy way to switch between distributed and distributed next if you would like to be able to do those cool things. Again, see James talk in like 20 to 30 minutes about this. Something else that we're trying to do in the realm of just making things easier on users is parsing more things that users want to be able to express. So normally Dagger at spawn has been kind of rigid in what it supports, really just basic function calls, and that was restrictive for quite a lot of use cases. So what we decided to do is let's teach the parser to be able to handle these more complicated things, say, broadcast, do blocks, things like name tuple construction, get property, indexing, get index, set index, and all kinds of stuff that you can see here on the screen. We're also taking a look at the possibility of implementing support for generators or list comprehensions, begin end, which if you've used threads.atspawn, this is what threads.atspawn does. It's just a big block of code. We want to be able to support that with @spawn. And potentially for loops, what would that look like? I don't know. This is something maybe we need to discuss.
So in an effort to make parallelism easier, we developed the stencil macro that I've just mentioned in the first slides also. And you basically can set your boundary conditions for a neighboring access via a wrap or a padding call, where you can pad with zeros, with ones, or any other number you want. And essentially what you're seeing on the screen right now is a very basic convolution that works distributed on many GPUs and multi-node, and it can work with MPI with the features that were just mentioned. So the main goal here is to provide a very common operation in HPC, which is stencils and even convolutions, through a simple macro. You just call the data depths, spawn data depths, you see in line 7 right here, and then from that the stencil is performed right out of the box.
All right, so Python integration. Maybe you could tell what I was going to talk about just from reading the title. So many people have expressed interest both within the Julia community and outside the Julia community about having closer integration between Julia and Python and other languages. And there's no reason that being able to access libraries like Dagger should be difficult from other languages. We should make this easy for users who really just want easy parallelism. So what we've done over the past year is putting together a very simple package, or very simple library in Python called PyDaggerJL. And what this basically provides is just a very simple set of bindings to Julia through the Python call interface, which allows you to do things like spawn Dagger tasks, fetch the result, and wait on these tasks. Now, this is very basic. You can build things with this, but obviously there's quite a lot more in Dagger that we want to expose. D-arrays, data depths, really the whole thing. So this is very much work in progress. If anyone's interested in cross-language integration, please reach out. And it's not just limited to Python. We're also looking at integration with C++, R, MATLAB, whatever seems interesting to people.
Now with the bunch of computer science features you just saw, we wanted to also provide numerical linear algebra researchers, or basically anyone who wants to perform numerical linear algebra operations, with the opportunity of doing so in a performant way. And if you ever venture in the wonderful world of numerical linear algebra, you may know that you should want data or specific blocks of data inside a matrix to reside in specific parts of your computer. So that would integrate with the fancy parallel algorithms you were using by tiling, basically. And we've managed to provide that inside Dagger when you basically create a D-array. So the calls you're seeing there, you're basically doing a 1,000 by 1,000 matrix with that specific tiling called in blocks, and you're assigning it with the well-known data distributions. So block cyclic, block row, or cyclic row, or any other common distribution you would want. We do support just 2D distributions. There's work to be done for 2.5D and 3D distributions, which are the fancier ones. So help wanted in this also. And as I've mentioned, if you want to implement these fancy parallel algorithms, you also want the underlying kernels you would call for each of these algorithms. And currently, due to the linearalgebra.jl package being tied to the BLAS/LAPACK implementations, we were not able to find it, or we were not able to build JLLs that would be easy to use, basically. So Rabab had this wonderful idea, which is the icon you see that is not me in the screen, to create a new package with pure Julia implementations of all the operations we needed into kernels. So they are native linear algebra kernels. Where it's needed, we do offer kernel abstraction support, and we do implement the fancier kernels. So TS or TT, which is triangle on top of square, or triangle on top of triangle, which is needed for these intricate parallel linear algebra algorithms. And going to the main slide for linear algebra is we are implementing also the parallel algorithms for it. We currently have the matrix multiply, the non-pivoting LU, both the LU with row pivoting and the QR or the CAQR algorithms are being implemented, are almost ready to be launched. Matrix inverse, linear solve, and SVDs are future work to be done, and they are pretty performant, I would say. And they also work for MPI and for multi-GPUs and any other architecture you will have.
Go ahead, sorry.
And last but not least, we do provide we call this the fastest Fourier transform of the moment just based on the FFTW. However, it's just a way of calling it like the Dagger-powered 1D, 2D, and 3D stencils we have. And we have support for slab or pencil stencils, which are basically a plane or a deep row into a 3D matrix or a tensor. And they work well with the common GPUs, CUDA or ROCm. And they were tested to work with MPI. So it's still a work in progress. We still want help. It was basically an effort made by Senna, who is also here. And that's it, I think.
Yep. Because I know we're a little bit early on time, I just want to say that this work is still, all of this work is still ongoing. There is a lot of availability right now. We have the framework, basically, that we need for writing highly parallel algorithms in pure Julia. What we need right now are people who actually want to write those algorithms. So, you know, we've got the FFT, we've got some linear algebra operations, we've got this and that, and these are the basics, and most of these are implemented in about 10 lines of code. I mean, it's literally that simple. Our Cholesky algorithm is like 15 lines. And it's the kind of thing that is able to beat OpenBLAS in many settings. So what we really need right now, though, are more people who are interested in writing these kinds of highly parallel algorithms for their specific domains. You know, these algorithms do not cover everything that people want to be able to do. Even this FFT is really just the basic FFT call on, you know, a 1D, 2D, or 3D input matrix, and that does not cover a lot of cases. So what what I'd really ask is if anyone out there is interested in just giving this a try and writing an algorithm in Dagger, in DataDeps for their application to be able to really speed up your application code, please reach out. We can provide guidance on how to write these algorithms. It's really quite straightforward. And we'd love, if you're interested in contributing those algorithms to Dagger, we'd love to have them. So yeah, please reach out on Slack or just come find us here. And thank you.
Is there any overlap between what's going on in nextla.jl and accelerated kernels?
Yes, so the answer is technically no right now. So just for background, accelerated kernels provides essentially GPU-capable algorithms that are for essentially like your basics. So MapReduce, sorting, things like that. NextLA is targeting more linear algebra specifically. Our goal with NextLA is to target GPUs for nearly all algorithms, and it may make sense for us to actually use accelerated kernels to implement those algorithms. And I mean, if accelerated kernels wanted that code into its core to be provided to everyone, that might be a possibility. But they're, not to use this word, but it's synergistic. They, you know, one provides the basics, one provides a linear algebra, and we would hope that also for other domains, people are going to do kind of the same thing we're doing with NextLA. But yeah, we're really focusing on linear algebra because we actually need those. For example, for Felipe's communication avoiding QR algorithm, there's quite a lot of algorithms that we do not have written in Julia in an accessible place, such as linearalgebra.jl, they're just not there, that we need to implement this. Additionally, for algorithms like the SVD, we do not have the algorithms we need. And so this is an effort to really push forward and get those algorithms implemented in Julia so we can start making progress on the bigger algorithms that everybody really relies on.
I just have a quick question here. So what is the foundation that you built this on? I mean, I'm a little naive on some of this, but is this kind of like channels for the parallelism, or do you just kind of like make your own thing, or is this writing on another like aspect of what Julia already supports for parallelism?
Yeah, so this is, that's a great question. So the foundation of Dagger is everything flows through a unified task model, and that task model is built on top of things that you are familiar with if you've used Julia for a while, which are Julia's built-in multi-threading support. We just use threads.atSpawn essentially, distributed.jl or distributednext.jl. We call out to the GPU libraries for GPU support. It's basically a multiple dispatch trick. Dagger just moves the data to the GPU. It calls QArray or RockArray or whatever it needs to do, and then it just calls basically the same operation, expecting Julia to then do the dispatch to a GPU-capable algorithm. So we really try to build on top of the things that are already in Julia. And you mentioned channels, so our streaming support is built not on channels, but on somewhat on remote channels, but also some custom implemented logic for performance. We have a ring buffer implementation that we use for buffers, and there's stuff like that, but effectively there's just a remote channel between nodes. And so in that case, that is kind of closer to using channels. But yeah, for the most part, multi-threading, distributed.jl or distributed next, and then the GPU backends are what we use.
And it supports communication between the multiple threads? So if you have recursive routines or things that rely on each other that you still want to parallel, they can talk and get their values back and forth?
Are you saying like nested multi-threading where you call like a Dagger algorithm and then one of those inner operations is multi-threaded?
Right.
That does work. You may not always get the best performance, especially if we're talking about BLOS, because BLOS has its kind of its own threads and they compete with Dagger. This is a problem not just for Dagger, but also for other libraries which do multi-threading and then call BLOS. But for like a threads.at threads loop should work fine.
Okay.
Yeah, there may be some considerations there. You may want to rewrite some of it to use all Dagger for everything, but it should still work fine with good performance.
Okay, excellent.
Yeah.
So I'm also have recently just started getting back into the multi HPC GPU game. There's the Vulkan library. Is that supported as a backend?
Vulkan, you said?
Yeah.
Not yet, but if you're interested, we can make that happen.
Okay.
This is also maybe an appeal to the audience. In addition to algorithms, what would really help us in the data centers if people start to contribute applications. It could be small applications, it could be big applications, but it is much easier for me to make my case to my supervisors that we need more staff to help Julian et al. If there are users who, you know, are sending, and you can do just send tickets saying this doesn't work, right? But like tell your HPC centers, here's an application, it's built on Dagger, it's built on other Julia technology, it doesn't work, or it doesn't work like I needed to, and that will actually help us get the resources. And in that context, I'm actually also wondering, Dagger is approaching, especially with streaming, it's looking like almost like a workflow manager. So have you started thinking about AI and integration of like, you know, multi-application workflows using Dagger?
You're talking about, I'm a little bit confused about the AI part of that, but are you referencing like AIDA, like those kind of workflow managers?
The things that we are predicting that will be a pain to implement properly, and so users will probably do horrible things like, I'm going to use the file system to mediate how things work together, here's my modeling and simulation code, and here's an AI code, and I want my AI to like build a surrogate model for like some part of that simulation. So what you ideally want is something where you're doing some mod sim, and then you can call out to an AI to do some, you know, I don't know, surrogate modeling or some training, and you don't want to go through the file system or, you know, do horrible things.
Right, you essentially want data transfer and synchronization not happening through the file system, because on supercomputers and other HPCs, that's absolutely a mess, performance-wise especially. Yeah, I mean, that is definitely something that we're interested in. There is a Dagger-powered workflow manager called Waluigi.jl that was put together, and that seemed to work pretty well, but development hasn't really taken off at all. We are interested in this. There are a lot of opportunities. Streaming is one of those features that could benefit from this or could work well with this in certain cases, like high energy physics, for example. But I would say even just the basic task model would probably work well for the case that you're describing. We should probably talk more about like what applications look like and what their needs are to kind of figure out what would be the best API, and is there anything missing that we need to implement.
I also have a question. On the fourth slide, you allocated CUDA arrays and then called distribute on them. If you use that pattern, are you limited to arrays that must fit on a single GPU, and does Dagger also then have to duplicate the data to send it to all the workers that you have, or different devices that you have available?
That's actually a good question. Basically, when we did this example, we tried to show like, okay, this is one way of doing it. But if you declare it through Dagger directly, the short answer is no. Like, you don't need to have data that fits into one GPU. In this specific example, there is more for like teaching purposes, yes. Generally, no, because generally you wouldn't declare it as it's declared right now. You would call directly into the Dagger interface, and it would distribute it by default.
Thank you.
And, oh, sorry, go ahead. I was also going to add that we are towards the multi-GPU and the, considering GPU VRAM front, which we both obviously have to deal with. We are also taking a look at adding explicit memory awareness to Dagger's data depths so that even as we're distributing things across multiple GPUs, across multiple ranks or nodes, we are keeping track of how much VRAM is actually available. And if we're starting to exceed that amount, we will slow down certain operations or essentially pause certain tasks or just not launch tasks that will allocate more VRAM, or we can move data around within data depth. So we can move data wherever we want. We have full control. So in that case, we're definitely taking a look over the next year to improve that support greatly, so you could just work on massive data sets and not even care. It'll work fine.
And to further the point, this will also play out with the work stealing suite we're developing. So if a GPU starts to get filled, basically, and another GPU has the bandwidth to take the underlying work or data, it will steal that into basically chunks of the DAG. So,
cool. Thank you.
Let's thank the speakers one more time. So now we will have 3 lightning talks. Right, so next, now we have 3 lightning talks. I think there'll be a little bit of time for questions, but I'm going to condense the question time as well. I give you 5 minutes. The minutes I show relative to the talk.
Okay. Sure.
So Rashid, take it away.
All right. All right. Hey everyone, my name is Rushil, and today I'm going to talk to you guys about automated algorithm selection discovery using LLMs. And a quick thank you to my team for making all of this research possible. All right, so a preview of what we're going to go over. So first, I'm going to introduce you guys to SmartSolve, which is what makes this possible. Go some of the motivation, the methodology, and how it sort of works. Then we'll go into the LLM aspect, how we use that to generate heuristics. And then at the end, we'll talk about integrating these heuristics into linear algebra workflows. All right, so why are we doing this? Well, linear algebra problems have many ways of being solved, and each approach can be more optimal for certain inputs. For example, you may see like 10 to 20 times speed up in certain algorithms depending on what input you provided. And there already exist heuristics by current linear algebra packages that attempt to solve this problem by partitioning the input space to certain algorithms. However, the main issue is that the feature space of all the inputs is really, really large because you have to take into account like all the possible matrix structures as well as the hardware, the precision you're dealing with, the algorithm, the format of the data. And so it's really difficult to develop a proper heuristic. And so what SmartSolve aims to do is have an automated approach to generating these heuristics. All right, so how does this work? Well, first we have a discovery stage. In this discovery stage, what we do is we take a list of matrix patterns, which we've gotten from like SweetSparse, Matrix Depot, and other matrix pattern repositories. And then we have a list of candidate algorithms that solve like a central problem. And then we run each of these algorithms on each of the inputs to see what like the time that it takes to perform each of the algorithms. We can then store all of this information within a database, a little bit more which I'll go on to later. And then we can have an LLM or some AI agent look at this database and analyze it to determine an optimal heuristic for algorithmic choice. And then lastly, we can take this heuristic and put this in other linear algebra packages so that users who use those linear algebra packages are able to use our optimal algorithmic choice. And an example of how this would work for LU factorization is, so there exist 2 default algorithms for LU factorization and some more specialized algorithms that work better for particular types of matrix patterns. And so we want to see, how can we choose which algorithm to use to do LU factorization based on the input we provide. And so we can run our benchmarking and discovery process by running each of the inputs for each algorithm that candidate algorithm we're dealing with. Then we can provide this benchmark to an LLM, which will look at this benchmark and determine, okay, now if I have a new input, how should I determine what the optimal algorithm will be? And it will do this by looking at the features of the matrix, information about the precision, and other important factors. And lastly, we would take this and put this into linear algebra software. All right, so what does this database actually contain? So one thing that it contains is the information about the input itself. And since we're dealing with linear algebra problems, this is information about the matrix structure and pattern. And so this would entail, the determinant, the rank, whether it's symmetric or not, just information to understand the structure of our matrix. Then we also contain information about the algorithm and architecture, like the time that it takes to run the algorithm on each input matrix and so on. And here's a quick example of what this benchmarking process would look like visually. And so here we have the Poisson matrix structure, and we run 4 candidate LU algorithms on this matrix structure. And so the default algorithm, which is dense LU, as we can see, it's 10 times slower than a lot of the specialized algorithms. And so if we have some sort of heuristic that tells us, oh, instead of using this default algorithm, let's use one of these other algorithms instead, we can achieve massive speedups, which is important for really large matrices. All right, so now this is the fun part. How do we actually generate the heuristics? And so we're going to utilize LLMs here. So the way we do this is we provide the database as a prompt into the LLM. And this prompt is split up into 3 sections. So the first section is we define the model's role and objective. And so by this, I mean we tell the model, hey, you are an expert at LU factorization. Can you determine some sort of optimal heuristic by analyzing this database? Then we actually provided the performance database to analyze, and then we specify what the output format of the heuristic should be. In our case, we detail it as some sort of decision tree made up of if and else statements for 2 reasons. The one reason is because it's very readable, right? If I have a bunch of if-else statements, I can sort of tell what's going on, how is the model making its decision. The other reason is also fast to compute, right? We don't want computing the heuristic to be a really large overhead. And the reason is, it already takes time to run the algorithm. If it takes a long time to decide what algorithm to use, then that just defeats the whole purpose of, choosing the more optimal algorithm. So yeah, then we can take our heuristic generated by the LLM, put it in some linear algebra system, and then we can pass in the linear algebra features, such as matrix features, such as the condition number, rank, whether it's symmetric, and these will be taken as inputs into the heuristic, which will then decide what the most optimal algorithm is, and then perform that operation. And as a quick example of what this would be, this very simplified version is this example here. So the heuristic is simple. We just check to see if it's banded or not. And if it's banded, then we convert the matrix into a banded data format, and then run this banded LU factorization version. Otherwise, we run the default factorization version. And the hope is that checking to see whether the matrix is banded or not, the time that it takes to do that is not as significant to where running the banded version compared to running the LU, normal LU version, there's a huge difference in that time. So if we go back to this graph here, right, we would hope that the time that it takes to check if it's banded is much less than 9 times the amount it takes to calculate banded LU, which it definitely is. Okay, so now let's talk a little bit about integrating our heuristics into the linear algebra ecosystem. So there already exist a bunch of linear algebra packages in Julia. One example is linearsolve.jl. And so what we could do is we could provide these heuristics into functions that users call in linear solve. And under the hood, when a user calls a function in linear solve, it will use this heuristic to determine the optimal algorithm and then actually run that optimal algorithm. But this isn't just limited to Julia, because we can apply the same idea to other languages like Python and MATLAB, which each already have their own heuristic. But again, like developing the proper heuristic is really difficult to do since, as I mentioned before, the feature space is really large. And so the hope is that by developing these automated heuristics, we can, change the whole linear algebra ecosystem by making these optimal choices. All right, so yeah, thank you guys so much for listening. Yeah.
Thank you. So I have a very quick question. Is the output of the LLM heuristic still in the form of decision trees?
Yeah, so the LLM outputted heuristic, it's just a Julia function basically, and this Julia function has inputs as the matrix features, and then the inside the body of the function is a bunch of if-else statements. So it checks like, if the size is greater than 10, then run this algorithm, otherwise run this algorithm.
I see. So how does this improve upon just using traditional machine learning to form a decision tree and then generate a code?
Yeah, that's a good point. So the main idea is one, customizability. It's really easy to tell the LLM like what you want the output format to be, and you can also include it to make it like actual Julia code. So you can just take the output of the LLM and just run that as Julia code. Where for a decision tree, it may not be as simple. The second reason is LLMs are evolving really rapidly, and so they're able to detect patterns at a much higher rate, more complex patterns than maybe a decision tree might be able to do. And so maybe it could be the case that decision trees are better, and that's what our current algorithm, if you look on our GitHub, that's what we have right now. The LLM is what I'm working on at the moment. So maybe it is the case that decision trees are much better, but I have a feeling that since LLMs are constantly improving, I think it's a worthwhile investment to at least try LLMs and see how they improve. Yeah, good question.
A very short question. You said the LLM are getting better, so which one are you using? Which model?
Yeah, so I can talk a bit more about this offline, but right now I'm using, Ollama to download LLM models locally, and when I ran these efforts, I used Llama, I think I used CodeLlama and Llama 3, but I'm trying to use other LLM models to see if they perform better, just trying to figure out which ones are the most efficient.
Okay, no, don't worry. Do you have an HTML? Yes. How about oh.
Seems to be working. Oh, we see the presenter view. Oh, yes, now it's perfect. Well, okay, so the first is right.
Well, hi you all. I'm Eduardo Franco. Today I'm going to talk to you about a little bit of how can integrate manifolds on GPU and physics simulations, okay? Symmetry X is currently a package we are developing, and it stands for a motivation that when I was in college, in the first years, we are working on with these deep man equations, and finally we arrive at the equation of motions. And at the time, we could visualize this kind of stuff, but when you dive in a little bit more and get into more complex physical systems, the hours waiting for the code to run and the tedious stuff, it became a little bit tired, right? So when we dive into a little bit this, we discovered GPU, Julia, and obviously high performance computing. And that's why when you start to code a little bit more, you understand that these capabilities are raising the infrastructure or physics simulations. So integrating this with CUDA.gl, we decided to create certain types of kernels which contain each the geometry of the manifold, and then we apply the physics inside of them to make some kind of simulations. Right now, you are going to see a little bit of the simulations we have working on and how we can apply this to more complex physics. And well, of course, this will motivate all of you to, well, in fact, try this package. The first one, we have like a charged particle on a torus. This animation runs like in under 2 seconds over 1 million steps. 64 particles around the crater of the torus, which with initial velocity, you can assignate the position vectors, the velocity vectors, and the charge vectors as you wish. In this case, we are just having you some kind of the equation. Here, you can imagine, like, could be plasma physics or condensed matter 1D lattice. This because of the ring you are seeing these approaches an harmonic oscillator and the normal modes of the torus. Also, you can identify another kind of structure, the ellipsoid, or where here you can see how it's a self-organization system where the system tries to balance out the charges. And, well, in fact, this is not only applies to classical physics, this will also apply to soft matter. If you can interact with this kind of particles at colloids, it will be another kind of physics. Also, I've talked about the manifolds, but you were seeing the 3D representation. In fact, the 2D manifold of the torus is just the theta and phi 2D space. So what the program does is the kernel, in fact, do the simulation over the 2D space, and then just plot it or transform the coordinates to the original space.
Does the physics depend on the embedding?
Of course. The embedded of the, no. The physics depends of the metric of the system. Yeah, right, I forgot to mention, the manifold is like, you can imagine the manifold as a surface of the structure that locally is flat, but in general is curved. So all the physics, all the interaction will be changed of this the structure. In fact, the space-time is also a manifold, right? So we are working on implementing also this kind of physics. Not just the interactional physics is on the surface, it could also be an external surface, like this with an external potential A, that could also interact and modify the trajectories of this structure. This not only applies to Lorentz models that you are seeing here, but also to active matter. Active matter is a solid chain of physics, which involves also a little bit more like the Brownian motion, and this other potential could be like interactions of the surroundings, right? Not only we have particles, we also support some kind of fluids or any kind of quantity that we want to see how this works under the surface. This not just applies to water, well, to fluids, but also could be some gases. That's why statistical mechanics can also be used in these examples. You can take the entropy as the curved heat, and then you can understand what is happening around the curvature. Finally, other of the other examples are the Boltzmann-Lattice-Boltzmann method. It's another kind of algorithm to improve some kind of stochastical mechanics systems. And also this runs on GPU. All these experiments that I'm telling you right now runs in less than 2, 3, 5 seconds in a GPU, which is a 450 in my computer, and it doesn't require a lot of complexity. Yeah, it's just for, it's in fact a wrapper around the CUDA.gl, but it adds the physics around it. So right now, Symmetry X is just like this little package. I'm working on it, but tomorrow we are expecting to add more manifolds, more geometries, and eventually more physics to make well, this kind of knowledge more democratize this kind of knowledge. And also, all these systems that you see, they are already a connected paper to one of them that already have been published by some authors in the past, but we just like recollect it. Thanks.
Hi, thanks for such a wonderful talk. So I was curious, here do you really need the GPU speed up because you're simulating on a manifold, or is it more so because you have some large number of particles you're simulating?
Yeah.
Or both, maybe.
Yeah, that's right. In fact, if we try to simulate each one of these systems, the CPU could be worked on, but the time complexity and the time that you are waiting for the results and the visualization will be very much upper, right? In fact, if we connect this with GLMACI, at the time the computation is doing the simulation, it in real time is displaying the image, okay? So it's a good question, but the GPU accelerates these computations, and it doesn't need or requires, in fact, a GPU, but it allows us to make this much, much faster.
I have 2 questions.
Okay.
First, you mentioned CUDA.jl.
Yeah.
Is this limited to CUDA, or did you use also kernel abstractions or something like that?
No, at the moment it's just CUDA.gl. We were working to use also kernel abstractions, but we didn't have the computer on, and also didn't have the metal on for Mac, so we couldn't make it. But in the future, we try to improve this to add those kind of GPUs.
And my second question is, have you looked at problems that are so big that you need to use some distributed computing and break them up across nodes?
Yeah, that's why, because, for example, if we look at take for example these 256 particles, it's a matrix of these particles with each one representing 2 vectors of the position at the time at the manifold, just theta and phi, and also its velocities, right? So this increases, this matrix increases at the time where the particles increases. Evidently, we have float 32 allocated to just 1 particle at a time, so we will need more than 3,000 particles in some simulations to overhead the capabilities of a GPU. But in theory, we could make some statistical models like gases corresponding on these ones with millions of particles, and then, yeah, we will need some dynamic allocation on other GPUs. But you haven't done that yet? No, we haven't done that.
Do your manifolds have to be 2-dimensional?
Sorry?
Is it only 2-dimensional manifolds?
At the time, the only 2 geometries we support, yes, is the ellipsoid and the torus, but rising up to other 3 or 1-dimensional is just reconnecting all of the other stuff. So it's not that hard, but yeah.
All right, let's thank the speaker one more time.
that did not go the way I expected it to. Thanks, guys. I can like barely see this from over here. Okay. So thanks everyone for coming. Today I want to talk about a library that me and Julian have been working on for the last little while called Distributed Next. I'll start with a little introduction. Let me page down. Right, there we go. Okay, so I work at a research facility called the European X-File. We basically operate a giant laser and scientists use it to do experiments. And my job is to help the scientists convert the data that we record into something that's scientifically meaningful. And Julian, well, you already saw Julian's talk. He works on Dagger and AMD GPU.jl and like a million other things. We originally met when we were both working on Dagger. And along the way, we started discussing distributed computing and that kind of thing. And that's how I got involved with distributed. So for those of you who, yeah, that's right. So for those of you who are unfamiliar with it, distributed.jl is one of Julia's standard libraries. And it's designed to do distributed computing. It's based entirely on RPC calls, so remote procedure calls. And the idea is that if you add a worker, then you can then make some arbitrary call on that worker and have the result returned to you. So it's kind of like it exposes a very functional interface. You can call arbitrary functions and get the results. This is quite convenient, but it also means that distributed requires that each worker has its own, has the same state. And it's kind of old as well. I don't know the exact date when it was created, but it's been around from nearly the beginning of Julia. I want to say something like 2012 or 2013. There's a little demo up there of what the API looks like. And distributed has some limitations. So Julian already spoke about the thread safety one before. An issue was opened for this lack of thread safety like 4 or 5 years ago, back in 2020. And the actual fix for that thread safety issue wasn't like horrendously complicated. There was a PR that was merged fairly quickly. However, every time it was merged, there would be hangs in CI. And distributed is used for running the tests of Julia itself. So if those tests hang, that's kind of a disaster for the whole language, because then development will basically stall because you don't know if it's distributed causing the hang or your PR is causing the hang. And so out of caution, this PR got reverted, and I think it was merged and then reverted like 2 or 3 times until finally, this year we finally got it over the line. So in Julia 1.12, distributed will finally be thread safe. Yeah, well, that doesn't display very well, but there we go. Distributed will finally be thread safe. But you know, that problem wasn't solved back when we started thinking about distributed next, and so this was one of the issues we had. Another issue is poor communication performance. So, like I said, distributed is based on remote procedure calls. It does have abstractions. It does have one abstraction called a remote channel. And naively, you might think, or at least I thought, that maybe a remote channel would have like some kind of optimized implementation, since you're only doing like a limited number of things. It doesn't. It's actually like every operation on a remote channel is also based on remote procedure calls. And last night I did some little benchmarks of the performance. And you can see that for a local channel, we get something on the tens of nanoseconds, which is not too bad. For a remote channel that's on the same process, the performance is not too bad. Like, it's a couple times worse, but there's still 0 allocation, so yeah, not too bad. But as soon as you go to a different node, it's like 1,500 times slower, which is a little unfortunate. Now, admittedly, some of that overhead is probably coming from network traffic, but still, 1,500 is, you know, quite a big factor, and I'm sure that there are things we can do to improve this. You'll also notice that we have a lot more allocations now once we go to a remote node. Another issue is the development pace of distributed. So like I said, distributed is a standard library, and oh my God, I'm running out of time. It's a standard library, and so the barrier of entry is kind of high because, you know, it has to be somewhat high quality. The people who can review distributed PRs are very busy, like horrendously busy, and distributed itself is not particularly easy to get to grips with. It's not that the library is bad designed or anything. Distributed computing is just a hard problem. And so the end result is that PRs are kind of slow to get merged, and the development process is quite slow. And so Julie and I decided a little while ago to try making a soft fork of distributed called Distributed Next. This is, it's a soft fork. And the idea is to make it a separate package so that we can play around with some ideas for improvements to distributed that might actually get upstreamed in the future. What else do I have up there? Oh yeah, I also took the opportunity to clean up the code base a little bit, which should make development a bit easier. Distributed Next shares the same API as distributed for now. And so if you want to support both distributed and distributed next, you can do that fairly easily. This is what Dagger does, for example. Basically, you can set up a preferences system and load either one or the other depending on the preference. If you do this, just keep in mind that distributed and distributed next are completely independent modules, so you can only use one at a time. You can't like remote call a distributed worker from the distributed next function. Okay, that's not gonna work. And I quickly wanna go over some improvements. There've been like a whole slew of bug fixes we've made to distributed next. Some of those we've also upstreamed to distributed. This is actually also why the thread safety support in distributed.jl was merged in time for 1.12. Along the way in CI, we came across like a ton of hangs in distributed next, and we managed to track those down to some lingering tasks. Those were fixed, we upstreamed them to distributed, and now we finally get thread safety, which is extremely cool. One of the cooler features is that distributed next will try to automatically figure out which is the fastest interface on your machine if you have a Linux system. And so if there's like if you're on a compute cluster and you have like a control network versus InfiniBand, it will automatically try and pick the InfiniBand network now. I'm probably running out of time, so I might go very quickly through these.
You have time. We can
I have time?
shrink the next bit a little bit.
Okay, cool. There are some plans that we have for the future of distributed next, and we're also very open to your ideas as well. One of them that we've come up with is some optimized implementation for remote channels. So you saw before that there was like a 1,500 times performance hit from communicating to a remote node. And here's an example of an alternative implementation that could be type stable and have 0 allocations. So the idea is that instead of relying on RPC calls for operating with remote channels, we could actually set up a separate I/O with its own interface and port for each channel, and then we could spawn a separate loop for this channel. This would be specialized on the element type of the remote channel, and the idea is that this should provide a much faster implementation than what we have now. That's one option. Another thing that we're discussing, oops. right. Let me see. Okay. Another thing we're actually working on at the moment is support for worker state callbacks. So sometimes when you're working with like a bunch of workers and you're adding and removing them or something, you want to get some kind of notification or have some operation happen whenever they are, brought up or brought down. This is what worker state callbacks are for. This is just hanging around in a PR that I should finish soon. And I remember now, I actually skipped over a slide, I think. Yes, I did. If you haven't seen it before, there is a library called parallelprocessingtools.jl, which was developed by Oliver Schultz. It's really cool, and it has this awesome macro in there called always everywhere. The idea is that you can put all of your imports and like your module loading stuff into this macro, and every time a worker is added, it will automatically run this, which is great because you don't have to ensure that all of that code is executed every time you add a new worker. This is like an awesome quality of life thing. Okay, I will move on. Another thing that we were thinking about is having better support for workers on different clusters. So imagine that you have like one worker on your laptop, then you've got some other workers on your compute cluster, and maybe another worker on your desktop. If you're SSHing to your compute cluster, let's say that the worker on your desktop wants to talk to the compute cluster worker. Well, right now, I'm not sure that would work because they would need to talk directly to each other, and maybe that wouldn't work because of the SSH connection or whatever. The idea is that maybe we can figure this out automatically and route all the communication through your laptop so that this is all seamless. That's just some of them. We do have some other ideas, which are over there. So a big one would be having type-stable interfaces and custom serialization. For those who are unaware, the serialization library in Julia is intentionally type unstable. So it has like these @ no specialized macros everywhere. And that causes allocations and GC problems and so on. There might be a way to add interfaces that are more type stable so we could improve performance there. Another one is observability tools, so like monitoring how much traffic is being transferred through workers and that sort of thing. A big one is actually cancellation. And here I actually have a question for you guys. Has anyone used distributed.interrupt? One guy. Okay, good to know. So I actually only learned about this function today. It apparently allows you to cancel long-running jobs. But anyway, we basically want to add better support for cancellation throughout distributed so that if you have like a remote call that's taking like a minute or something, you can safely cancel it and be somewhat confident that it won't break everything if you just hit Control-C. And if you have things that you would like to have in distributed next, we would also like to hear that. So in summary, we are working on distributed next to fix like bugs and adds, experimental new features that would be difficult to do in distributed. We're very open to suggestions. The advantage to working on distributed next instead of distributed directly is that there's just less overhead. It's a regular package, it's not a standard library, so it's easier to get stuff merged and to play with it. And a lot of the improvements and bug fixes that we've made have already been upstream to distributed. So like these bug fixes for thread safety, for example, and like some various other bug fixes that we came across. I would also like to give a shout out to the original developers of distributed because it is kind of an impressive library and a lot of work was put into it. And with that, I am done and would be happy to take questions. Thank you.
Hi, thank you so much for the work. The existence of a standard library distributed package was initially what brought me to Julia. The main trouble that I found with it was the performance. The architecture of it having a main head node, and then everything else being remote, especially compared to things like MPI. So when you want to go distributed, you probably want to scale to hundreds or thousands of nodes. How do you do in terms of performance? I love the quality of life. It's much saner than MPI. I mean, that doesn't say much, does it? But it's the performance that in the end makes you want to use distributed.
Are you talking specifically about communication performance, like the example I gave before with the remote channels?
I suppose both communication performance and also things like collective communication, the reduction algorithms and all the things that you get from MPI.
Yeah, so in that sense, I think distributed is somewhat lower level than MPI. It doesn't support any of the collective operations in MPI, and for that sort of thing, I think you would maybe want Dagger instead. When it comes to communication performance, I think we just have to work on it to make it better. It's definitely much slower than MPI right now. Like you saw, it took, I think it was like 60 milliseconds or something to transfer one integer from one processor to another. There's something going on there. Right, so so the conclusion would be it's probably quite lacking compared to MPI when it comes to communication.
My question is more related to the architecture. Sure, you can build higher level tools like reductions and collective communication on top of what you've made in distributed. Is there anything in the architecture of distributed that would make it not scale as well as MPI? I remember a while ago I asked Valentin Shoravi about distributed, and he said that he had some experiments where communication was able to be faster than an MPI because you can serialize while communicating, which is something that,
sure,
I think I'm remembering that correctly.
We also have a potential answer from the audience.
Go for it. Yeah.
So really the architectural issue of distributed is the 1 to n issue. MPI does somewhat have that issue because you do still have rank 0 doing quite a lot of stuff, doing a lot of setup. There are a variety of solutions. I don't think changing that architecture would necessarily work out very well. We still, frequently people are starting up distributed workers from their laptop from a REPL. You already have a REPL running and then you just add procs. Like that is, I think that provides a very nice interface. I don't know if we'd want to change that, but I do think there is the chance for optimizations, doing things like, for example, one of the bottlenecks for distributed is just like starting up 100,000 workers because you need to start one and start the other, just communicate some stuff, and that takes linear time, which is not great. You can implement optimizations, though, that say starts up 4 workers and then 4 workers starts up 64 workers, et cetera, et cetera. I just think no one has really gotten around to implementing those, but there has definitely been talk that that is something that we can do to get around a lot of these issues, to bring loading or to bring startup time down from insane levels down to manageable levels. And there's a lot of optimizations that we can apply that just have not yet been applied, that still allow us to have this architecture and also scale to MPI level numbers. Yeah, I mean, people have done it before. You can ask Viral Shah at Julia Hub. I know he's done quite a lot with distributed. He was one of the original maintainers back years ago. He and many people at Julia Hub have pushed distributed to levels like that, and I'm sure they have war stories. So I would ask them how that went. But it is something we're interested in working on, absolutely.
It would be amazing to have the performance of MPI and the usability of distributed. And being able to use a REPL, have an interactive session while having MPI workers.
Right, and just to repeat it would be great to have essentially the power, like the power and scaling of MPI, but with the conveniences of distributed. And yeah, completely agreed. And I think that's really what we're driving towards. I mean, we're looking at HPC use cases and thinking like, how can we meet the existing HPC ecosystem with distributed?
That was the original hope of distributed.
Absolutely, yeah. It just
And then people sort of gave up after a while, and it's wonderful to see people like yourself coming back and doing it again.
Yep.
I'm going to shamelessly add my own opinion at this point and say there are so many applications using MPI, and then you ask the user, do you want to use MPI? And I almost always hear a resounding, hell no, but it's the only thing that works and has performance at the level that we needed. So I mean, look at PGAS and things like that. We would love to use that, and then it doesn't work at scale, right? And so, anyway, this is merging with the panel, by the way, but maybe we will first, if there are any other questions specifically for James, we can ask them, otherwise we can start merging into the panel. All right, let's thank James one more time. All right, so in true, yikes, this is very sensitive. In true Julia fashion, there's a just-in-time component. The organizers asked me yesterday when I was really busy doing the tutorial, how about organizing a panel? And so what I'm planning to do now is, who are the speakers that are still in the room? Please raise your hand. All right, we've got 1, 2, 3, 4, 5 folks. Well, Sam, you should have, you were a speaker. So there's six folks here. And also the room, of course, isn't set up for panel-style discussion, which adds technical difficulties. What I propose we do is those speakers that want to be on the panel, and please feel free to want to be on the panel, please come down and we can have a panel about Julia for HPC. And if you don't want to, then I'll start volunteering you. All right. Maybe the right algorithm here is, so there's a couple of chairs, maybe you sit on the table. No, oh, okay, yes, perfect. All right, so we are just gonna pass around the mic that's down here, excuse me. Okay, I'm just, yeah, we have one audience mic, so we're going to do the. Oh wow! I hope I'm insured when I break this thing. So maybe what we can do is like, so let's sit on the chairs. Well, we don't have enough chairs. All right. I'm going to check if it does reach. Okay, perfect. All right, so before the audience questions, my warm-up question to the panelists is, it's my standard warm-up question, so people might have heard it before, but what should the Julia for HPC community, if like you could name one thing, what should we be focusing on? And I will volunteers to go first.
Well, I think David and I might say the same thing, but garbage collection of foreign memory is a big problem, in my opinion, and until we can solve that, I do not think Julia on HPC will really be competitive with other languages.
Yeah, I agree that, but I would not say it's not competitive because of that it is. We can still work around it, but it would be very good to solve this issue, yeah. Because we end up sometimes just deactivating the garbage collection. And that works if you really control how much memory you allocate, etc. But for other applications, like who do fancy things, it might not work. But also, just to follow up on the previous talk, I think the distributed, to have something like distributed instead of MPI would really be nice. But I wonder personally if it would not be possible to really just build something based on MPI, because you have so much functionality in there. You can create communicators, merge them. You can really do a lot of things. So you could maybe build something like distributed based on MPI.
Provided the vendors actually support all of those features that they said they would support, but don't eventually, make it into the standard. So anyway.
Yeah, so going back on garbage collection, one of our talks, we presented Q-numeric JL, and we've talked with the Dagger team in the past, and we both share the same issue, that the garbage collection of foreign memory objects within Julia it's not great. Because Julia just doesn't know about these external memory references, because its heap heuristics are based on Julia managed objects. So the ability to register these foreign objects is, I think, something to be discussed, and something at least the four of us could agree on. Maybe other people that work on CUDA JL or AMD GPU JL, that is something that will enable HPC within Julia.
Yeah, big +1 to foreign memory and GC. It is a massive problem that affects nearly every HPC library, except for ones that use MPI pretty heavily. It's less of a problem, but it still ends up biting us in the butt quite frequently. I know AMD GPU, the current head maintainer, Anton, has been working on a lot of like machine learning, machine vision kind of problems, and until he implemented basically hacks in AMD GPU to deal with this issue, he was not able to run real problems in Julia, and that's not okay. I mean, how are we going to be at the state of the art if we can't even run, what is basic demos? I think that's kind of crazy. So I agree. This is a huge focus.
And to expand a little bit on the point, I think that not only garbage collection of foreign objects, but cross-language integration in general. Because I don't know if anyone faced the same things, but sometimes you want to build a wrapper from Julia or to Julia, and then you say, okay, we have these cool things like cxx.jl and etc. But then you try to build some parallel or distributed thing, and there's a little caveat everywhere. Like, I want to do multi-GPU. But then you kind of can't, right? Like, I think there's a gap in general, not only for GC of foreign objects, but like functionality in general, like the way that Julia plays out with C++ in distributed settings is something, and the way that Julia plays out with GPU integration with C++ also. So that's a thing we think we want to bridge the gap.
A +1 on that, with our library, we decided to make a C wrapper to our C++ interface. So that, I mean, we feel that.
Is that not a C++ problem?
Yeah.
Yes.
Kind of both, I think.
It's a both problem.
Yeah, it's a both problem.
More tightly coupled integration would be, I mean, I'm saying broad things, like how do you actually do something?
One other thing that I think could get improvement would be debugging GPU code. That it has gotten quite a lot of improvement, but it's still not as nice and easy as with CPU code at all, right? Yeah.
Away from the mic. All right, so we've had already a great start of a discussion. Are there questions from the audience? Right.
I don't know if it's a question, but just to follow up on the MPI versus distributed. I'm not sure how much the issue is that MPI is so bad as a programming model, but kind of as Sam was saying, that like, I think there is some room for just improving the developer experience. And one thing that I've been like also having chats at previous JuliaCons is that it would be really nice to have REPL or notebook-like tools that that you can easily use with MPI. That you can like, for me, my dream would be in Pluto that I can just like set at the top MPI processes equal to 4, and then like each cell will run on each MPU process and give me the 4 outputs. And like, I don't think that exists in any ecosystem. I mean, there's some like running like, with Tmux panes, like, but I think like just having more interactive tools to work with MPI would be really great for anyone working on these parallel codes.
So I'm going to use this as a little bit of an excuse for why. The reasoning for that is what happens if you do an MPI collective operation. What happens if you do an MPI collective operation is that you have to wait on other ranks to go do stuff, right? It's collective. The problem is, what do you do while you're waiting? Well, in MPI, it just sits there spinning in a circle. It does not yield to Julia's scheduler. It does not allow us to do anything useful. Can we start other threads? Sure, we can do that as a hack. Can we do all kinds of things that are hacks? Yes, we can do those. But the problem is that the MPI, the way MPI is implemented and the guarantees that I guess the standard provides are just not enough for modern day concurrency. I mean, you reference the REPL, you reference notebooks, those are highly asynchronous environments. Dagger is one of those examples, but even just talking about the REPL or Jupyter, if Jupyter, for example, has some MPI integration and say it's, you know, doing some stuff in the background, the moment you hit an MPI collective, well, all of those things come to a halt. And now MPI is kind of putting you in a bad place. So not to use that as an excuse, though, there are things that we can do. MPI Cluster Manager, for example, is one of those where it provides a distributed .jl interface over MPI, and that actually can work really, really nicely for code that you want to write in a distributed style but still gain the benefits of MPI. And also, I mean, we could probably do something where, I don't know, we run on each MPI rank something in the background that connects, you know, provides a REPL on each rank. Maybe that's possible. People need to investigate this. I mean, they need to try it out and see if it's feasible, but just beware there are problems with, you know, integration between async and MPI that'll come up.
So if you want to do MPI in Pluto, you can check out Valentin Churavi's RSC course on his website, and he come up with a MPI macro where basically you can put in a Pluto notebook, and under the hood is spawning an MPI process or like a. So it's nice because you can write your code in the notebook. Of course, it's running somewhere else. So it's a hack, but it's a nice hack, I will say. So if you want to really use MPI in Pluto, you can try this.
Further to that, the MPI cluster managers looks fantastic. We would really need that. I don't think it's in a usable state right now. Are you currently using it? Okay, last time I tried it, it had some like pre-compilation issues that seemed to come from the library itself. If I'm wrong, I'm very glad. Thank you. I'll investigate that. Yeah, it seemed that it was like from the library that needed a bit more maintenance. It hasn't had any commit in like 3 years, hasn't it, or something like that? Yeah. Okay, but yeah, maintaining that would probably be my call. It's great. It's a very nice interface and a very good middle ground. Thank you.
And to kind of like to further the point, I would say that at least from my experience debugging MPI while using Julia, is so painful. It's so painful. Like whenever something breaks, it's so bad. So I think there's room for improvement there also, for quality of life. Like it's so bad. Like things break and it just starts popping up like, whatever, whatever, JLL, and then you don't know where that points to. That's so bad for me. I would say so. But at least in C++, that's where you use MPI outside of Julia, but I would say so, like, oh, thank you. Like, when things break in Julia, I don't know if that's a wrapping issue, but like, these stack trace is one of, yeah, yeah.
And just having better integration with like symbol translation to figure out what these Julia objects are.
Yeah, it kind of gets lost in the wrapper there, and then you don't know what's happening.
Right. I guess I do want to then ask the panel, we just spent a bit of time talking about asynchronous MPI. Is the Julia HPC community doing enough to bring some of these ideas back to the vendors and the the standards developers, because these are ideas that would benefit other languages as well, in your opinion?
I mean, I don't know. Also, everything that I'm talking about is anecdotal, obviously, but you are met with quite a prejudice when you say, okay, I'm doing this and this and that to someone that's involved. At least I've talked with people involved in the MPI standard before, and like I do this and this and that, and they say, oh, okay, this is a known issue, and then you say, in Julia, and they say, yeah, whatever. Like, they basically do not give attention enough, I think. But like, we can do a better job at communicating that, obviously, but I think it's the same way you guys mentioned, like, is that a C++ or a Julia issue? I think it's both. I think they don't want to hear it, and we do not communicate that effectively.
Yeah, I think it's also, the situation is maybe similar to the one that we have with NVIDIA and CUDA.jl, where NVIDIA kind of sometimes cares, but usually most of the time doesn't really care about us. They care about C++, Fortran, and especially now Python, because that's their big thing. And, you know, I feel like on the MPI side, they're also similarly interested, maybe not so much in Python, but they really care about C++, Fortran, like the existing languages, because most of the big MPI codes that are out there that are functioning fine are written in those languages, and they really just appear to care about that. Like, what would they do? I mean, are they going to go back and revise the specification so that now, oh, there's a way for MPI to yield back to Julia? Maybe. How many years are we going to have to wait for that? I mean, you know, 5, 10 years, I don't know. These things move kind of slowly. I'm just not confident, so I personally rather put my eggs in the distributed basket and see how far we can go with that, but provide MPI support where we can.
Now that you brought up the snakes on the plane again, what continues to amaze me is that let's say the promise of efficiency that Julia brings is completely ignored in machine learning these days, and in my impression is that it doesn't even, like, it even loses momentum. Like, it isn't catching up, it's losing ground. Why is that in your perspective? Or is that true? Maybe the first question.
Are you asking, is Julia losing ground in machine learning compared to Python?
That is my impression. Like, the number of Python libraries for machine learning is growing more rapidly than the number of machine learning libraries for machine learning in Julia. Yeah. I would argue that this is the same at this point. Or let me rephrase this, everything that people use NVIDIA GPUs for, more people using Python, and more Python exists, right? TensorFlow, JAX, PyTorch, like the number of libraries and the number of lines of codes that I could site is growing faster than the number of lines of code, I could side with Julia. I have opinions, but that is something different.
I think I don't use machine learning all that much in Julia because my impression is the same as yours, that Python is far ahead of it. And from what I've heard, that multi-node, like distributed training in Julia just isn't really all that great. And if I had to guess, it's related to this garbage collection issue because you're doing AI training, that's going to use a GPU. And if you're doing distributed training, you're probably using a lot of memory, which, as we've discussed, Julia is not great at cleaning up. So you take a big performance hit compared to something like a Python library. And then just some anecdotal evidence. I was at Argonne last summer, and they have the Aurora supercomputer, which is Intel. And the group I was in, they loved using Julia, but they just they couldn't really run their machine learning workload on Aurora because it was using Intel GPUs. So they're not going to spend the time to like work for a month or two to develop this thing in Julia when they could just use PyTorch, and it kind of sort of works on Intel.
I think that answers it like on the technical side, but I would say that this is a very much social issue. Like when you mentioned they wouldn't spend 1 or 2 months trying to build that, we should have a community that already built those basically. So I think this is not only a technical question, but a very much social one. Like how do you expand community, or how do you convince people to build these features that are supposed to build them? Because like we know for a fact that AI specialists or ML specialists, however you want to call it, they don't want to build these things, and they shouldn't, obviously. So how do you convince people from like other or with no community to try to develop Julia further? Like that, as I mentioned, this is a very much social issue. It's a convincing issue.
So I've been listening to this discussion for the last, 15 minutes about MPI and Python libraries. And one thing that I keep thinking in the back of my mind is that the number of people who use HPC is dwindlingly small. People do not use HPC. So the fact that everybody in HPC is doing this is irrelevant to me because it's not very many people at all. To me, the right question is how do you get a lot more people to use HPC? So instead of focusing on MPI or not MPI, I think HPC community has missed the right question for decades. How do we get more people to use HPC? I believe, I'll give you my own answer to this, is we have to make it a lot easier to use. And that's hard work, right? It means don't focus on performance like we've been doing for decades. I mean, don't ignore performance, but don't focus on performance. Make it that these things are usable for the undergraduates that I teach, the graduate students that I teach. These folks don't want to use HPC. It's too much of a pain. So I think that's the right question, and I'd like to see a lot more of that.
While I'm moving the mic, y'all can answer.
And I think this is kind of cheating to answer your question because this is an ongoing discussion on every FIRE meeting. But when you look into Python, it was built exactly to be easy to use, as we've mentioned 1,000 times already, and it gained traction exactly like that. Like you started an intro course for computer science or whatever, it's Python. It's always Python. And then people started getting acquainted with it and building a community with it, like newcomers started coming, and that built the entire ecosystem for Python. That same argument can be used for HPC. That same argument can be used for AI and Julia. So this is also, I think, your own point that I'm bringing up. So there's that. It's some way of bridging the usability gap, and I think things come naturally from that. So as I mentioned, a very much social thing, and this may be one of the solutions. So bringing in newcomers through being easy to use, HPC or Julia or any technology that comes from it.
So to address the issue of like, how do you get more people to like utilize HPC resources, right? One of the main focuses of our presentation that we gave earlier today was basically you have one CPU code. That same CPU code should be able to run across multiple GPUs. It should be able to run across multiple nodes. And it's just the exact same code without any modification. I showed a git diff. It was like 7 lines of code for an entire gray sky heat diffusion application. And those 7 lines of code change was just, instead of using, yeah. Yeah.
Now we've got to get past stencils and matmols and, you know, the basic dozen things that
Yeah.
HPC is good at to make this really work.
Just quick, and then you can say something. So in our talk, you had basically said that you want like people to be able to write arbitrary code, and it just runs on HPC.
As a fantasy.
Yeah. So I say there's like fundamental issues, like scalar indexing a GPU array is just always going to be a bad idea. So like fundamentally a for loop that's just indexing on a GPU, you're going to have a pretty smart compiler to figure out that you can just completely remove that loop and replace it with an array operation. And if it's not possible to do that, then your performance is kind of just going to suck. So I guess it would be possible to run that on a GPU, but it's not going to have good performance in the end.
Yeah, I guess to get more people use Julia for HPC, I guess we need to do really, really well, not only as well as Python. So we don't need to only make things simple or whatever, but be so much better to get people to change, to switch to Python, because people always come, why should I switch? Is it really worth it? But I think we can, right? We can, because we have the performance argument in addition. We can say it's as easy as Python or even easier. That's always subjective. But if you have the performance in addition, you can say it's 10 times faster. Then people will change more easily. And to come back to the other thing about AI, I believe there one could maybe also get more people to switch to Julia if we can improve the still further the usage of Python from within Julia. Of course, there are good tools like PyCall, Python call, but it would still be possible to improve. If it would be really just as easy to use Python from within Julia as from Python itself, if there's these conversions, etc., of data types or whatever, it would be just kind of no problem at all. Then I think also the AI people could more easily be attracted.
And this is my way of cheating, of getting next again. So I like your point that the perception is there's not a lot of people using HPC, but I think that this is currently changing a lot, because in the last only like 1 or 2 years, there's so many open weight large language models, generative AI models been released that people really start to build their own, let's say, 2 GPU cluster, right? And it's, on one perspective, this is not HPC, right? 2 GPUs on 1 mainboard, or maybe like 2 mainboards or like a mainboard and an extended GPU. But getting 2 GPUs to run like something halfway decent for the average hobbyist, this can be very difficult. I know because I have tried, and I'm not the best HPC programmer. And like this could be a good moment to try to capitalize on this, that here is something that might be readily usable, that might solve the 2-language problem and all those things, if we think a lot smaller what HPC might mean.
I'm actually really glad this topic came up because I'm not an HPC user. I'm a data scientist. I do machine learning, big data, etc. And one thing that I've noticed just listening to a lot of this is that there's a lot in common with HPC actually, but it's, I think, easier to achieve than HPC in many ways. For example, someone earlier mentioned if you're using distributed.jl, you want hundreds of workers, but that doesn't work very well right now. But for me, you know, doing big data, at work I use PySpark, unfortunately. But if I were, let's say, using Julia, I could instead spin up distributed.jl, spin up threads, and now I instantly have way more power available to me than what PySpark gives me, and that's a massive industry standard right now. And Julia's already, between distributed and threads, basically beating that, and then you get a better interface with something like Dagger. And so, yeah, I was actually thinking, kind of doing this whole thing, it's also interesting to see what Julia has achieved, even if it hasn't maybe reached those HPC levels. A much larger amount of users aren't doing HPC. They're doing AI, they're doing ML, they're doing, you know, big data, whatever. And for them, actually, there's a lot of potential in the infrastructure that already exists in Julia. It's not usable yet for HPC, but it's basically already there for ML and stuff. So, yeah, that's all I wanted to say.
Yeah, I want to add to both what you said and what you said. And so I know there is this feeling among HPC people, like people who have been through the HPC gauntlet, they've done all the hard work, and you know they've scaled on like the world's biggest supercomputers. I'm not pointing at you specifically, but there are people who I have spoken to who feel like the term HPC only gets to be applied to certain scales, to certain hardware, to certain kinds of problems, but that's really silly because what does HPC stand for? High performance computing. High performance computing can mean anything from a supercomputer down to just running on a single GPU on my laptop or a 2 GPU system. Like why do we consider them different? It's all the same thing realistically. It's all the same Julia libraries for the most part. Like I can use parallel stencil on a supercomputer, but I should also expect to be able to use it on my laptop. Like that's a reasonable assumption. Same with qnumeric.jl. Like I would expect that I can develop on my laptop and then I can deploy as far as I want. And if it's only, you know, a 4-node cluster or something like that, a few GPUs, that's cool. It's still HPC. So, you know, the distinction between, oh, this is HPC, this is not, it's a silly distinction. It's like, it's really just created from the fact that there is a kind of semi-isolated community at, you know, national labs and academia and stuff like that that do their things on very expensive supercomputers. But they are not only HPC. AI people, data scientists, like just regular people doing simulations, they're all doing HPC. It's all high performance and it's all computing. And I think, to your point, like, it should be easy for you to just spawn up some distributed workers, start some threads, and beat the pants off PySpark, because it really does suck. And we have everything we need for that. I think we maybe just need to put ourselves out there and like maybe put together some example code, put together some marketing materials, and just be like, yeah, PySpark kind of sucks. We can do it better. Here you go. Go ahead and take this code and run with it. I think we are there.
Yeah, I'd just like to bounce back on the very first question, what could help improve or spread out HPC and Julia, and there was a couple like obstacles that stopped the momentum. You mentioned garbage collection, cross-language integration, and from that question we went on to the like HPC and Julia should be more spread out once again, and so one of the solutions that's been offered would be to actually teach it in classes, and actually there's a presentation that happened this morning about generating papers directly from Julia and generating Pluto notebooks and so on. Would there be any other solution? Maybe I'm thinking, because Felipe mentioned, a lot of the time there's issues, I guess debugging MPI, for instance, and then it's just, oh yeah, we know it's there, but I feel like maybe if there would be more documentation about those issues, or if that documentation would be more made more available, maybe we could find people from around the globe to solve it. Maybe you see any?
Yes.
Tuition.
That was a very good question, by the way. I think this is all the previous questions can be clumped up in a balance of interest and bandwidth. Like the AI people that want to use Julia as is and want to clump up the building blocks to do it, or the data scientists, whatever, the application scientists in general, they can do it, but some people don't have the bandwidth to do it. I think that these are very known issues for a while now. There hasn't just been the interest and bandwidth to solve them. And I say I can clump up many of the questions here because to Alan's point, this is also a very hard problem to do. Building compilers that solve these issues and to improve the debugger that works in JLLs with MPI. But I think that's the literal first step to like solving this problem of interest and bandwidth, because people know the issue, but building minimal working examples that cover all of them and all the edge cases is very difficult. So if we could, as a community, get together or in a project and just document these extensively, we would solve a bunch of problems. Not saying that the problems themselves are like trivial. No, they aren't. As I've mentioned, the compiler thing that may solve the problem of running in a computer in your laptop or an HPC cluster could be solved, but it's a hard problem. Like documentation helps, but it's not the only thing. It's the first step, I think.
Thanks. And here I want to issue a call to action, and maybe specifically get it to if people are watching at home live or later on the YouTubes. There always seems to be a perception that open source is done by these experts who do incredible work, and then they present like those really clever stuff. And then there's people like me who sit here who have no idea what they're talking about. But I encourage everyone, people as naive as I, go to the packages, download them, and if the minimal working example doesn't work, then open an issue, and then help, like, just giving the feedback of, oh, I got stuck on step 0 or step 1 is already starting to contributing. And then you can help contributing the documentation. Oh, I'm completely new here, and this is what I had to do additionally. And I wrote it down, it's 2 lines, but it helps, and it's these little steps. Everyone is invited. Please be cordially invited.
Yeah, and also I know there is a big barrier to filing, not filing issues. That's a little bit easier usually, but like contributing documentation, contributing examples, just to submitting any form of like a pull request or something to packages. It has gotten a lot easier over the past few years to, submit changes. I mean, you go into GitHub, you click on a file, you click the edit button, you type your changes, and then you click like 2 buttons and there's a PR. Like, if we're talking about documentation, you don't have to get it right the first time. Your documentation does not have to be stellar. The fact that you're even putting in the effort to just try to improve things is so much appreciated by package maintainers, because we just don't have enough time. We don't have enough focus on those specific issues that you're encountering, and we want you to help us out and just you know, add some documentation or even just file issues. If all you have time for is filing an issue, that's great. If you get a chance to come back around and actually go fix that issue, even more appreciated. And it's really not that much work. And if your first, you know, pass of documentation kind of sucks, there's typos and, you know, punctuation's out of order and the spacing's not perfect, who cares? We can fix that for you. We can just push a fix up, or you can fix it later. Like, it doesn't matter. Just like, if you find something that's broken, that needs fixing, that just needs announcing, just do that. Don't be quiet about it. Let us know and just work with us, and we'll work with you.
And to make your case stronger, also, a little story. I came up to Julian 2.5 to 3 years ago. I was an application scientist, and I said, oh, this looks cool. I want to do that. And all of a sudden, all I did was say, hey, what does this do? What does that do? This is breaking. And then through that, he not only fixed the issues that I was having, but I learned from it, and I am a part of the, I think I am a part of the community now. So it's good to have people that know nothing, which was my case, poking things, like, and having them simply explode. And then I went crying to Julian, and that was fixed quickly. And that was like, testing by the developers is done, obviously, but it can not be extensive enough as a user doing their thing and breaking stuff. So this also makes your case for like first step documentation, or first step issuing, or first step slacking, like send a Slack message, hey, this doesn't work at all, fix it.
Just one short thing on that. I believe that extends also to feature requests. I mean, we want to know what people are missing, right? And it's likely that you're not alone who is missing some feature.
So we have a queue of 3 more questions, and I think that's the end of the queue. So please, last questions.
Right, thank you. I was really interested in the question of Professor Edelman about the adoption of HPC and how easy it is to get into it. I would be very interested in hearing more specifics, as in at what level do you encounter these problems? Is it accessing HPC resources or the arcane knowledge to get it running, or is it something Julia specific, or all of them? I would say that most domains have trouble with adoption of HPC resources, including in C, C++, and Fortran. I would say even more so than in Julia. I mean, it's a bit of an arcane knowledge, isn't it? You have a few HPC wizards at every university, and then that's kind of it. So, again, I'm really interested in specifics. Where do you think the problems are in terms of that make it hard to adopt HPC and HPC stuff? Thank you.
Yeah, so one of the aspects of HPC in Julia is just the community in Julia in general, expanding that, right? With a stronger community, just like how Python has this very strong ML backing, right? The more people that work on these type of problems, the better support you could have for HPC libraries and resources. So just like Julian was describing problems with documentation and stuff like that, a stronger community will enable us to have better documentation. It will allow users to write this HPC code that will work on HPC clusters. And you mentioned access to HPC resources, right? It's for this particular presentation that we gave, we've had access to a single node cluster for the credits that they gave us. So unfortunately, we didn't even have scaling results ourselves on multiple nodes. So that is a huge problem. Getting access to just multiple nodes can be quite difficult. And that is something NERSC tries to resolve. It is a hard problem to get access to these people.
My impression is no. So like I've used MPI 4Pi and like HDF5 in Python, and my impression of the documentation is it's just like, it's very bare bones, and it's kind of just like, good luck. Like we wrapped it, but we're not really gonna tell you much about how it works. So it's possible, but my impression with Julia is that it's much easier. So like the implicit global grid library, we benchmarked it in our thing, and it took me like literally 5 minutes to figure out how to get it to work, and it just kind of worked. So my experience with Julia has been that it's much easier to get HPC running than in Python, save for maybe machine learning applications.
Yeah, I don't actually think that using HPC with Julia is difficult or more difficult than with others. It's just the opposite. I believe it can be very easy. And I think it's just about education. So at ETH, for example, we have a master course that we give, and the students love it, and these people afterwards start projects, start a PhD, use Julia. So this is really an effective way to get people. But well, it's just one course, right? This should happen all around the world, and it takes time.
So we have a question from the audience. I just want to, because we're close to the end of the time, so please, James.
I want to briefly go back to this topic of getting new users into HPC. My impression is that when we say things like high performance computing is easy in Julia, that's kind of only focusing on like part of what a user gets to experience, because when a user gets started with Julia for the first time, maybe they do some computation or simulation, but then they want to plot stuff. How do they plot it? Well, maybe they install plots and they try to run this inside iJulia. Plots, so Plotly, the Plotly backend, which allows for interactive plots, was broken in iJulia for like the last 3 years or something. If you want to use Maki, that's also great, but it's like horrendously slow. And my point is that there are so many paper cuts, these little paper cuts along the way to actually doing your HPC, that's probably going to turn off a lot of the less serious people. I mean, I don't want to say less serious, the less hardcore people. There are groups who get funding to do their compute on, you know, supercomputers. Those people are probably gonna be motivated enough to push through and get stuff done. But for the hobbyists, I mean, I think they're probably just gonna give up. And so my point is that I think it would be very useful if we kind of went through the process of implementing a complete example workload from start to finish in Julia and see what problems we come across and then try and fix them. My approach was to become a co-maintainer of iJulia. That was maybe a bit too far, but you see the point.
And on this point, I want to pick up two words that you said and that you just said. So the user experience is really, I think, the key of unlocking these things, like thinking about how people come to this thing. And like the typical biography, I would say, is there's a student who gets tasked with doing something cluster in the basement of a university, something. And then there's this one helpful admin that gets them started. And then there's a PhD student or a grad student or what have you, and they also help them along. And now I get back to what you said. Slack is a tool in Julia that cannot be understated, I think, in terms of importance, because Julia has a super nice community, in my humble opinion. And just to give you an example, before I came here, like even though I am somewhat, I gently nudged my way in, and I'm now actually running a podcast on Julia Dispatch, if you haven't heard it. I am not the expert Julia programmer, but I messaged a couple of people before coming here, hey, I want to talk to you, and everybody was like, oh yeah, cool, let's do it. And so please reach out, especially all the younger folks, undergrads, also all the hobbyists, like everyone, all ages, all everyone reach out to anybody in the community, and people are very enthusiastic and polite. I think, for instance, the Pluto notebook, the success they had is, I think, mostly due because they use a lot of emojis and they make it very, very clear how supportive and how encouraging they are. And I think everybody is that way in the Julia community, as far as I can tell. They're just not showing it as extrovertedly, let's say.
I don't know if anyone or everyone realized it, but it's kind of a very circular motion that we're doing since the beginning of the panel, or since the beginning of the discussion, between like the adoption of Julia or the adoption of HPC. Like, it's circular in the sense that we need something to be easier for more people to use. But for something to be easier, we need more people working on it. And it becomes incredibly circular, and I think we need to find a sweet spot on where to break it. Like, and as the developers, the only control we have is, unfortunately, by doing the hard work, in the sense that we need to make things easier inadvertently, I think. Otherwise, the circle argument will not break ever. So, as James mentioned, this is a good one, like building a workflow from start to finish, seeing if things break, seeing if things are easy, not only for us, but for like people that are not well acquainted with our own packages. So as I've mentioned, it's time to break the cycle, basically. Like, oh, we don't have that many users, so we don't have that much, like that many features. But we don't have that many users because we don't have that many features. And the only way we as developers can break it is to like try to make things easier. Like reaching out to the community, I think, is good, definitely. It's great, but I think won't solve the problem in and itself.
Yeah, I mean, I think the big issue with Julia that I find, particularly in astronomy, is is just the marketing issue. It's a cultural issue. I mean, we cannot get money to do Julia in astronomy. It just goes to Python. That's partly my fault 25 years ago for helping develop scientific Python. But I think in terms of getting Julia in high-performance computing, you know, I've been speaking with the people at our high-performance computing center at my university. They were not aware of Julia. And once I told them about it and its benefits, they're excited about it. And the point is that if you have these easy tools and we can tell them about it, then when people come to them and say, I want to do computing, they say, well, you might want, instead of using Python, you might want to think about Julia because we can actually get you up and running quickly, and you can use the older GPUs or APUs to solve your problem instead of high performance, you know, the newer stuff. So, you know, it's marketing and getting the word out to people and showing them the benefits of it. That's, you know, that's what I keep doing over time.
Yeah, and exactly. Greater marketing increases the amount of users and more people working on these libraries and strengthening the community, and more features come about that way. People submitting more PRs because some features broken. Documentation increases, and that just overall impacts the community in a great way.
Hi, I'm Michael Ferguson. I work at Hewlett-Packard Enterprise. I've been working on the Chapel programming language for the past 15 years. So I'm here representing a different community. Luca and I are doing a BOF on Chapel, and Julia tomorrow at, assuming tomorrow's Thursday, because I can't think, at 2:30. So I'd love to see you there. And Chapel is a language designed for distributed memory programming. I am winding up to a question, which is, in Chapel, we don't really think, like our sort of viewpoint on distributed memory, HPC programming, is that MPI is too hard, and that's the problem, and we need something else. So my question to you in the panel is, do we have any Julia components that you're aware of that use high-performance networks that don't go through MPI?
Like, I think Dagger, do you guys know? Or you use distributed? For us, we have an agnostic backend, meaning our runtime with Q-numeric JL could use UCX. It could use, it supports nickel. Of course, you could use MPI as well. So it's up to the user to figure out what they want. I don't know about other Julia tools.
There is UCX.jl, which has not gotten enough love, but it deserves more love. I want to also point out that there are very scattered research projects. So if you want to, like, I'm happy to work with you about this.
I think another solution besides distributed and Dagger, etc., are also packages like implicit global grid, which I'm developing, which uses MPI to create something very simple for a particular kind of problems, right? In this case, Halo updates, and we need to do standstill computation. And then it's dirt simple to use it. And so you have all the performance of MPI, but not the difficulties with it.
I will second that. Implicit global grid is dirt simple to use.
Yeah, I mean, we showed a graph, and you guys destroyed our performance for our greatest copy diffusion.
Last question, I promise.
All right, I just wanted to bring up and ask you to draw some comparisons between your experience and what I like to say about the experience in the JUMP community. So we had like a big twist in both like quality and maintenance and going ahead of the project. As soon as non-focus went in, we had Oscar full-time on that, and we had all these nice plots where the issues just dropped. And so there were a lot of enterprise support. I myself was paid some hours in the company I used to work for. My supervisor was one of the core developers, so we had a team that contributed to JUMP, and we saw this coming back as it worked best. As JUMP came to a point where we were even able to integrate this with MPI and to distribute it and JUMP together. So this is super nice. And on the other hand, we had some partners in academia that were starting to teach optimization courses in JUMP. And it was super fun because students didn't even know Julia, but they knew how to use JUMP. And we're not using AMPL anymore. We're not using other things. And when we told them, oh, you can just like do data frames and everything, the language, they were super excited about it, and they already were using it on a daily basis. So I was just curious about how strategies like having full-time developers backed by grants and also teaching courses that are not exactly introduction to programming, but some specific, either like linear algebra or some other close to HPC activity.
I definitely agree that we had talked about this a little bit before, but like getting in on the ground floor and like teaching undergrads, grad students to use Julia. So I know at CMU, a couple of the people that use Julia, some of the professors, they teach it as part of their class, and now all those students are exposed to Julia. And there's maybe not as clean of an example as JUMP in my field, but getting people exposed like that is definitely one of the solutions in my opinion. And maybe it's just like an exponential growth, and we need just like enough people to start doing this to actually see an effect. But yeah, I can't predict the future, I guess.
One thing that's good is trying to bridge other communities. This is a weird question, but are you Brazilian? I thought so. The thing is, there's a small, like really small Julia community in Brazil, but it exists. We're trying to push a Portuguese first book in Julia for like CS 101. So I do agree that the basal courses are the gateway to Julia. Like, as I've mentioned with Python, like people start using Python and then they start like getting acquainted with it, and it's the first language. Like, I still can write C code, pure C, because even though I haven't touched it for 4 years, that was the first language that I learned computing, and the concepts are kind of engraved in the way I do things. So it's also a problem with learning a second language. When you learn a Latin language, it's really hard to learn a non-Latin language. And the other way around is also true. So if you start at doing something, it becomes natural to you. So that's a gap to bridge. And again, the circular argument is that for that to happen, we need to have the ease of use to present computational concepts through it, like through Julian, etc.
And with respect to resources, the University of Tübingen in southern Germany is heavily expanding compute at the moment, and they also have open academic positions. There is a small Julia community in the town as well. It will not be realistic that the compute resources that you're building up will only run Julia. Like, expect that you'll also have to do some Python programming, but I would still assume that, like, if you're planning to apply in the near future for PhD positions, postdoc positions, that sort of stuff, Tübingen in southern Germany is very international and welcoming.
All right. On that note, I'm also German, so I'm not affiliated with Tübingen. I'm not strategically ending on that note, even though it's a lovely city. Anyway, I want to thank the panelists, the speakers, the lovely audience that has stayed 17 minutes past dinner time. So first of all, a big applause to everyone. Yeah. There will also be a HPC BOF on Friday, and again, it's wonderful to see the fact that all y'all have stayed around this long means that there is still great enthusiasm, and I'm also going to plug the HPC community call. There's a European time one as well, and you can find that on the Julia website. And with that, please, have a good dinner, and we maybe discuss some more later.
From the first phrase.
I couldn't stop looking at it.